Well, welcome. Survived 4 days of grueling class. Today's the 5th. And as you know, there'll be a final.
Where's the exit?
Yeah, I'll buy that.
Tomorrow at 6:30.
So as usually is the case, I begin my presentation with a warning. If there happens to be anybody listening to this or watching this that is not aware of the danger of being associated with this field, let me make it perfectly clear. If you work in the field, your career will be destroyed. If you are even interested in it, it has the potential for being damaging to your personal and professional life.
I just learned yesterday. Last Saturday, I heard Huizinga passed away, and so as much as I was frustrated, but now I wish him all the peace to him. So he has passed away last Saturday. Huizinga.
Let's take a moment and honor the passing of Huizinga. Okay. So, yesterday we covered lots and lots and lots of stuff, so much stuff that wouldn't even fit on a slide. We were interested in the issue of where the energy goes. We noticed from the earlier day that there are no energetic nuclear products, that helium-4 is measured in amounts commensurate with the excess energy. If the helium-4 is born with some energy, then we ought to be able to detect it using the Palladium deuteride as a nuclear detector. We went through that argument. We found that the helium-4, the alpha particle, is born with an energy less than conservatively 20 kilovolts, which has it with less than 0.1% of the reaction energies measured experimentally, at least in 2 experiments. So the question is where does the energy go? And turning to experiment, I proposed an interpretation of the 2 laser experiment. Shine 2 lasers on, excess heat stimulated, turn the 2 lasers off, the excess heat persists. But the idea is that maybe the excitation of the optical phonon modes at the difference frequency is causing the energy produced in the nuclear reactions to be drawn into the optical phonon modes.
Just a question. In that experiment, you used a 700 Gauss magnetic field.
Dennis Letts had noticed in earlier work that if you added magnetic field, it made it work better. And so he tended to keep the magnets there for all the other experiments in the hopes that it would make it work better.
You think it's necessary?
Letts had some experiments with the magnets not there, and those experiments didn't work in that series. Okay, so excess heat stimulated by deuterium flux. Deuterium flux, deuterium going from octahedral site to octahedral site, we argued is effective at creating optical phonon mode excitation. We identified the biggest theory problem as the fractionation of a large quantum, namely if you've got a MeV scale quantum and the energy is going into vibrational modes that have a small fraction of an EV, then the question is how do you take the big quantum and chop it up into many small quanta and convert the energy efficiently? And we found last time that the Lossy spin-boson model shows efficient coherent energy exchange under conditions of fractionation. In fact, we introduced a toy model then which was perfectly capable of taking a large quantum and chopping it up into as many small quanta as you like and exchanging the energy coherently. We were interested in the issue of collimated X-ray emission. primarily in the Carboot experiment, earlier observation by Gotze, and in the experiments of Kornilova and Vysotsky. So the conjecture there, the interpretation that I'm offering, is that this is an upconversion of vibrational energy resulting in nuclear excitation. In order to account for this theoretically, the Lossy spin-boson model being a toy model, we needed a full industrial strength model, and the coupling to produce nuclear excitation needed to be very strong, and that led us to a new Hamiltonian for condensed matter that includes phonon nuclear coupling. That Hamiltonian, although we introduced it as being new, in a sense it's not really new. It's the Hamiltonian that you would actually write down from the standard model if you wanted to include vibrational nuclear coupling, if you thought that a generalized fully Walthusian rotation wasn't going to rotate out the first order strong coupling, the strong first order coupling. Okay, so we're interested in a new condensed matter model. Before proceeding, let me emphasize that the ideas under discussion here constitute one line of thought, one that I've been following along with one of my colleagues. There are other models. There are many other models. There are over 1,000 theory papers in the field. The single most successful model in terms of gaining acceptance is the Whittam-Larsen model. My understanding at this point is there's more than 1,000 physicists and scientists that are now supporters of Whittam-Larsen. And it's sufficiently compelling that it provides the basis for an effort at NASA. So it's gotten a lot of press, so for those of you who are followed it or interested in it, there's lots of information available, but the basic idea is that in this model, electrons gain mass through interactions with excited plasmon modes, and gaining mass then it is available to take reactions which would normally go one way and send them the other way. So Whittam and Larsen proposed that this heavy electron can undergo a weak interaction with the proton, make a neutron, a soft neutron with the long wavelength they propose can make it to another nucleus and cause transmutations and do other things. So again, the single most widely accepted model at this point. Whittam's a particle physics, particle physicist with an excellent reputation, and again, I recommend that you, if you're interested, follow their papers. Kim's got a model based on a Bose-Einstein condensate, and Kim argues that you've got a way to overcome the Coulomb barrier directly in this Bose-Einstein model. His model has a lot of followers, including Def Callion, who's recently adopted Kim's model as an explanation for their nickel-hydrogen results. Preparata is a famous particle physicist in Italy, was a close collaborator with Martin Fleischmann. He had very interesting ideas about coherent energy exchange and, if you like, fractionation. Philosophically, the ideas I'm discussing here are reasonably closely related to the philosophy and ideas of Preparata, even though Preparata's been gone now for many years. His ideas are still extremely influential in Italy. Takahashi has a model based on essentially Coulombic collapse. The idea is that if deuterons or even protons and electrons in the classical problem, if they maintain relative separation, you can achieve a configuration where it's attractive. In the classical problem, it can collapse. He proposes that in the quantum problem, it can collapse as well. His model has quite a few followers in Japan and also elsewhere. And you'll find that at this point, there are models now appearing in the mainstream physics journals. A very good physicist who's recently joined the field, Mark Davidson, has had a paper accepted on this problem in foundations of physics, no less than foundations of physics.
Peter, you
Yeah.
mentioned, so the Whittam-Larson model, you mentioned transmutation, so that would be a cold fusion model? Be considered a cold fusion model?
I think Whittam and Larson consider their model to explain pretty much everything that happens in the field and things happening in other fields as well.
Okay, but it does, to explain the excess heat effect.
They claim it accounts for the excess heat effect.
So you mentioned that there may be a 1,000 scientific proponents of that particular model?
That's what I have heard.
Okay, so if there's 1,000, so I'm just trying to put things in relative perspective. So if there's 1,000 folks who follow, who support that model in some way or believe it, that would indicate there's 1,000 scientists or researchers who are acknowledging the credibility of the excess heat effect in the field. So I guess the question would be, if there's 1,000 people that are following it and feel it's credible, but the scientific community in general is not recognizing the field, is credible. How many does it take? How many more? If it's 1,000, is it 10,000? How many are there?
I don't know if there are 1,000. I've heard there's a very large number. I have met some of my colleagues who are very enthusiastic supporters of Whittam and Larson. Don't want to hear about anything else. So I tend to be fairly fanatical in terms of their acceptance of it. But I don't know if there's 1,000. I don't actually think there's any number that's sufficient in order to get the scientific community on board for being interested in this field. I don't actually think it's going to happen. Wow. Okay, let me go back along the lines I was arguing from the previous discussions. So excess heat in Fleischmann Pons experiment challenges textbook condensed matter nuclear physics. Carboot's collimated X-rays, in my view, present a similar challenge. There are many other anomalies. There's tritium production, there's low energy nuclear emissions, first reported by Steve Johns, observed by Kevin Wolf, many publications by Pam Voss and the Spay-War group, and anomalies which will be on our slides shortly that are not described by condensed matter and nuclear textbooks. To account for the collimated emission of Carboot experiment, using the approach that we've been focusing on, we found that we needed a very strong coupling between vibration and internal nuclear degrees of freedom, which led us to a new, but in a sense not new, fundamental Hamiltonian. Okay, so because we're having an exam later today, I wanted to present some equations which you're going to be responsibly tested on these. So this is a model that's used that you will find in the textbooks to describe condensed matter physics. And if you look at this, you should see a kinetic energy for the nuclei, kinetic energy for the electrons, repulsion between the electrons, repulsion between the nuclei, and attraction between the nuclei and the electrons. So, as we argued before, Hamiltonian is a very efficient way of letting you get to see what's in your model. Here's the Hamiltonian. We see what's in this model. And this model has been very successful since the 1930s, maybe in the late 1920s, in accounting for atomic physics, molecular physics, and condensed matter physics. There are different degrees of freedom in the model. There's electronic degrees of freedom. There's nuclear degrees of freedom. Electrons move much faster than the nuclei, so you can separate out the electronic degrees of freedom. That was done using the Born-Oppenheimer approximation ages and ages ago. If you use the Born-Oppenheimer approximation, you can get a new Hamiltonian that talks about the nuclear kinetic energy, repulsion between the nuclei themselves, and there's an electronic energy contribution. And this can allow you to isolate your attention on vibrations in molecules or solids, amorphous solids, or ordered solids, if you like. Now, in the new model that's under discussion, all of electron kinetic energy, electron nuclear, the Coulomb interactions are kept exactly as they were in the models in the textbooks. The only thing that's happening is that what used to be the kinetic energy of the nuclei is being replaced by a relativistic description. And the relativistic description basically says take QCD, take QHD, quantum heterodynamics, take whatever's your favorite model for the nuclear states, and solve for the energies in the rest frame, put them in a diagonal matrix, and then if you're going to move it, the center of mass motion is going to cause a coupling between these rest frame states. Boosted states, Lorentz transformed, it's modified, it's squashed, all these things happen. So that goes into a coupling matrix, which is off diagonal. And so this is the new description now for the nuclear states and the coupling with the vibrations.
Now, how big are these matrices?
This one's infinite in size. There's an infinite number of states if you're complete. In practice, probably you can get away with a subset of the states. So in general, it can be finite, maybe gigantic. If you're actually going to use it for a calculation, you might be able to get by with only using a few of the energy levels and a few of the coupling coefficients. So there's a route to be able to get numbers out of this kind of model practically.
And one more question is, are there any computer codes that allow you to, if you use a large number of matrices, solve these equations?
This equation is a formidable equation to solve, and at the moment there are no codes that's going to give you general solutions of it. On the other hand, for special cases, you can reduce it down to an equivalent Lossy spin-boson model. That can be solved, and I have solved such models. And it can be solved numerically, it can be solved analytically, it can be solved approximately. We've got all kinds of methods to solve it at this point. So practically, we can actually do something with this as a starting place. Now, before we talked about textbook model, we could separate the electronic nuclear degrees of freedom. In this new model, we can do the same thing. Here's the answer. For the nuclear kinetic energy, now we still have the more general description. Coulomb interaction between the nuclei, electronic interaction, or electronic energy. There's another term here, and the idea is that the nuclei are vibrating. You have the possibility of coupling energy to the electrons and promoting them and having energy loss. And so I've written in that as a loss operator, which is a way to keep track that that kind of thing happens. Probably we ought to remember it and use it in our calculations. You might say, well, you didn't include that in the last one. Well, could have. And in the textbook models, certainly phonon electron coupling is known and included and is described in the literature. So I would be on solid footing by including exactly the same loss operator in the textbook model, although people don't usually write it that way. It could be written that way. I'm writing it this way in order to emphasize that there is loss here, and the loss that comes about from that process is sort of exactly what you need to get a lossy spin-boson model out of the problem. Finally, as argued, it's possible to start from this complicated model and reduce it down to something simpler. So for example, if one vibrational mode is very highly excited, then perhaps the others don't do very much, so maybe we forget about them. So here's the highly excited oscillator vibrational mode, and maybe two levels are more important than all the other levels in your calculations. So here's two-level system, but many of them at the different sites. And here's the coupling between the vibrations and the nuclear excitation. Here's the loss. We have a lossy spin-boson model, which we can derive from our fundamental Hamiltonian. So the energy levels, in some cases we know them because they're in the nuclear databases. phonon modes, the modes and the frequencies are available in condensed matter literature. The way that the nuclei move in connection with vibrations is well known. That problem's in condensed matter literature. The coupling between different states, well, that's not quite as easy to get. Right now, we've not got such good models for that. On the other hand, in some cases, the coupling coefficient is similar to that appears in dipole transitions. So one can imagine, in some cases, of using approximation where one takes a dipole transition equivalent, uses it a first approximation for the mass-weighted equivalent, and off you go. So that there's actually a way to evaluate this and get numbers. Let me talk briefly about the issue of coupling to the radiation field. In a paper some years ago, I sent it in without any coupling to the radiation field, and the reviewers jumping up and down saying, well, radiation field comes in a certain way, you should add it in the standard way. So I rewrote some of the paper and I put that in. I said, well, you can add the radiation field in the standard way. A little bit later I started thinking about it. I thought, well, this works a little bit different. The different nucleons, they all have roughly the same mass, but they don't have the same charge. So when you're calculating these matrices, you're going to get one matrix for the mass, and you're going to get a slightly different matrix for the charge. So the form's sort of the same. It's not quite standard form, but it's close enough that we recognize that we can deal with it. So we now have mass energy coupling to vibrations, coupling to transverse radiation field, and then we've got in the Coulomb gauge the longitudinal interactions, the Bohr-Oppenheimer electron energy loss. Basically, we've got an adequate place to start. So there we go. And the adequate place to start, if you like, is it's not intended to be anything new. It's tended to be just an expression of standard model physics applied to condensed matter, including interactions between vibrations and internal nuclear degrees of freedom. To take away that message, textbook condensed matter cannot describe the anomalies. The proposal here is to upgrade the starting place to include coupling with internal nuclear states, and the approach suggested here is not one of reinventing physics or coming up with a new coupling interaction, new mechanism, new anything. The proposal here is just to take advantage of the physics that's in different textbooks. So the idea is that the new model in this discussion is put forth as being just simply a little bit better model than the one we had before. We don't lose any earlier physics. All the physics that's in the textbooks is pretty darn good physics, and we'd like to keep it. And using this approach, there's no problem with keeping it at all. In fact, we can derive the earlier physics directly from this somewhat more general Hamiltonian. And in the limit that the generalized Foldy-Wolthusen applies, we can separate the strong first-order coupling, and we get textbook physics. And the limit that loss prevents application of generalized Foldy-Wolthusen, well, we get into a new regime where we get new physics going on. It's this. The suggestion here is we now have the possibility of a systematic theory for treatment of basically all the anomalies systematically. Oh, takeaway message. I get to catch my breath. Questions, comments?
So,
do any of the other theories that you mentioned a few slides ago explain Carbu?
That's tricky. And the reason that it's tricky is because in some cases the proponents have argued that they obviously explain Carbu, and so I will put that forth as a response. I mean, in some cases I don't see it, but you know, I'm not them, and I don't have the insight they do into their models.
How possible is it that several of these might be correct? What you're describing here sounds like basically a careful derivation of physics, more accurately done. And that seems like, regardless of whether the other theories might be correct or not, this still seems like it's valid on that basis. So it's really a choice between yours and really which of these insights are all correct.
Your question's a great question. There has been discussion. Preparata had an answer to your question that he used to expound at conferences at very high volume. And Preparata's answer is that there's only one theory that can possibly be correct. Of course, what followed. And that's my theory. That was Preparata's approach and argument. The models themselves, the proponents of the different models do not recognize the theories as being the same. And if you talk to Whittam and Larson, they will tell you that their model is correct, and that what I'm doing is just, completely, off track. Takahashi will tell you that his model is correct, and that I'm just, I've wandered off into a regime that's unproductive. So I think the answer is probably no at this point. Other questions? Only easy questions.
Normally, if you have a good model or a good theory, you should be able to predict what may happen in a future experiment. Does Whittam and Larson have any predictions?
They have lots of predictions.
Okay.
And my understanding is that NASA's made an effort to follow up on their predictions.
Is it possible that using this theory to predict the production of X-rays in this environment?
I argued yesterday, towards the end when I was flipping through view graphs at light speed, 1 every 10th of a second, and talking at 3 times normal speed, I'd argued that we had our first indication finally that this new model appears to predict inverse fractionation, surprisingly relevant to fractionation observed in Karabout's experiment.
And also in these, we should expect X-rays also in the cold fusion experiment that is like in the nano.
A good question. Certainly X-rays have been observed. Having a fundamental Hamiltonian doesn't mean that all the calculations are done at this point. So your question's a good question, but I want to differ on the answer.
You mentioned other anomalies, tritium and low energy nuclear. What does Whittam and Larson say about these other anomalies?
My understanding from from what's been written by them and by others about the model is that it provides a comprehensive treatment of all anomalies systematically. I'm not familiar with the detailed descriptions as to how to do it and predictions from the models and so forth. I've read many of their papers, and I've written technical discussions of technical issues on their papers. But the claim is very general and very broad at the moment for Whittam and Larson. Okay, let's return now to the excess heat problem. So we now have a fundamental model that we think should describe excess heat effect. If you like the basic spin-boson model, Lossy spin-boson model says 2-level system, linear coupling to an oscillator. If the coupling's strong enough and if there's enough of them, you should be able to fractionate the quantum. Now the headache with the D2 to helium-4 transition is that it's hindered by the Coulomb barrier, so it's only weakly coupled. So it cannot be sufficiently strongly coupled to fractionate the large quantum by itself. So this was understood more than a decade ago with respect to these models. We proposed early on a more complicated scheme, which basically said let the D2 to helium-4 transition be a weakly coupled transition, and let there be another transition which is strongly coupled. So the idea is that the D2 to helium-4 would provide the excitation, the energy. It would be transferred to the strongly coupled system. The strongly coupled system would slice and dice it up, fractionate the quantum, and allow the whole thing to go. So this is called the donor-receiver model. We have a toy model, the donor-receiver model, that works this way. The model's constructed, it's analyzed, we understand what the model says, how it works, what it does. And at this point, in coming months and years, the idea is to take some of these ideas and models and connect it with the new fundamental Hamiltonian, and try to put everything together. Actually, some progress along those lines has been made, which I will point to as we go on. So the simplest theoretical approach using these ideas is to say, two-level system, D2 going to helium-4, 24 MeV quantum, highly excited phonon mode, fractionate the big quantum. So this is the first problem of this class focused on. And it didn't take very long to come to the conclusion that there was no way in the world that would work. So this one got taken out to the back, buried, another tombstone along with by now over 300 other tombstones. The donor-receiver model basically says D2 to helium-4, weak coupling to the phonon mode. Let's introduce another system, say another nuclear transition, which has very strong coupling. So the idea is that you start here, you make a transition down here, exchange one phonon. But this is a coupled quantum system, so the excitation goes over here. And when it goes over there, because the coupling's strong, this system has the possibility of subdivision and fractionation and reducing the large quantum into many smaller quanta. So here's what the associated Hamiltonian looks like. So now we have two sets of two-level systems, a donor system, a receiver system. We've got our oscillator, we've got our loss. And then we have weak coupling like we had before for the donor system, and we have strong coupling for the receiver system. So here's the model. And this model has been known for a decade or so to be able to work pretty much like what's needed, consistent with the scheme to get excess heat. In the strong coupling limit, we can get Ehrenfest type equations again. And we get a nonlinear oscillatory behavior, and we get a rate which has various terms. And these terms are interesting, we can understand them. Okay, I don't have the slide that I'm looking for, so I get to explain it here. 4v square root of n over h bar, this is the rate that you would get if the donor were perfectly matched to the receiver and there was no fractionation going on. E to the minus g is the Coulomb barrier, so you're going to get that for a donor transition no matter what. And what's going on over here is basically the receiver trying to accept the energy. So this is basically hindrance factor. And the hindrance factor is sort of the same idea for the hindrance factor for the Lossy spin-boson model. If the coupling's strong enough, if you have enough two-level systems, close enough to being on resonance, then it can work. But this also had some other physics in it. If you made a toy model and you calculate things out, it sort of looks like this. And you say, well, this is really complicated. What the heck is going on? Well, this peak right here is one that says the donor transition's got 151 quantum. The receiver transition's got 151 quantum, so the donor and receiver sort of are matched, and you get a resonance. But this one says, suppose the donor transition is 300 quantum, the receiver is 150, then basically what's going on here is that two receivers are being excited. So a big donor is transferring the energy, and now two receivers get the energy, and they slice and dice it up. This one's 3 and 4 and 5, and so in this simplistic calculation, what we're seeing is a subdivision effect. So instead of having to take the whole big quantum and chop it up by brute force, you can take it, you can subdivide it into 2 or 3 or 4, and depending on the parameters of the model can tell you how much subdivision you can have, and then you can have your fractionation. So this model sort of already has the subdivision fractionation, and again that was observed years ago when we first started working with these models. So the new model says strongly coupled receiver allows the donor to give the energy to the receiver oscillator system. Reaction rate's linear in the coupling matrix element. That's actually a gigantic issue because that means the tunneling factor comes in only once. So e to the minus g for the molecular D2 is 10 to the minus 35, but normal fusion is going to go like e to the minus 2g, and e to the minus 2g is 10 to the minus 70. So in the case of a molecule, the incoherent rate, the tunneling factor associated with it, would make the incoherent process be 35 orders of magnitude slower. So this is actually a big deal. I had argued last time that we'd wanted to maintain a coherent process, and this is actually the reason that we'd like to have a coherent process. This actually explains within the model how to overcome the Coulomb barrier. And if you like, we don't overcome the Coulomb barrier. We accept the Coulomb barrier as it is, but it just comes into the problem once rather than twice. The excess power rates in the new model, if you plug into a calculator and punch in numbers, the best numbers that you can find, the better the numbers are, the closer the rates seem to be to the experimental values, which is interesting. Takeaway message. Takeaway message. D2 helium-4 2-weakly coupled. Make use of different transition for fractionation. We've got a toy model that implements this idea. If the receiver can't fractionate the large quantum, there are no reactions at all. If the receiver fractionates the large quantum efficiently, then the rate-limiting thing is the donor dynamics, and we can evaluate that separately.
Is the fractionation the slow part, or is it the phonon coupling from the subdivision to the fractionation?
I think either can be the slow part.
Okay.
I think there are systems in which pretty clearly the inverse fractionation or fractionation is limiting things. There are other systems which look very much like the fractionation works about as good as it can possibly work, and the donor dynamics would be rate limiting. I think within the realm of experimentation already done, it looks to me like both limits are present.
Thank you.
Other thoughts or comments or questions? Okay. So let's consider some particular schemes. So we're thinking, have a theoretical picture now for excess heat. We have a toy model analysis that elucidates the mechanisms. So we have fractionation, we have excitation transfer. We've got a fair amount of stuff going on, but the models, they're not terribly complicated, and you can analyze and look at them and see how every piece of it works. Now we can turn back to experiment. The question is, can we identify model components of different experiments? I'm looking at this slide and I'm thinking, well, this sounds very straightforward. This sounds very simple. What the slide isn't saying is that this took a decade with a very large number of failures and tombstones out in the back. There were 4 major attacks on the problem, each one which went on for a year or more, identifying a candidate donor or candidate receiver system and analyzing it to death and having everything not work again and again and again. So I'm looking at this slide and I'm thinking, if you only knew. So at the moment, the schemes that are under consideration sort of look like this. Let's consider the vanilla Fleischmann Pons experiment. So the donor reaction sort of simply is D2 helium-4 transition. The receiver is, if you like, deuterons. Scratch and say, well, why deuterons? Well, if you think about it, the vibrational mode implicated in the LETS experiment is an optical phonon mode. And if you go and you calculate the optical phonon modes, deuterons are light, the palladiums are heavy, so the deuterons are moving, but the palladium nuclei are basically just sitting there. So if you're going to fractionate a quantum, whoever's going to fractionate the quantum has to be moving. So the only candidate in a PDD system then is the deuteron. So the question is, can a deuteron fractionate a quantum? So the new model was used on a transition in the deuteron, and we calculated the associated matrix element. At that time, we didn't have the full analysis. Looking back on it now, the matrix element we calculated was too small to do the job. That's because we identified a weak transition. On the other hand, the analysis gave us selection rules. The selection rules were really interesting. The selection rules said that basically, if you had a magnetic field and you oriented it sort of the way Let's was oriented and Mitchell was orienting it, that you get a big advantage, and that you should see a big effect having to do with the magnetic field. Now, transition is not the right transition, but the selection rules should apply pretty much to any transition with the same quantum numbers. So the transitions which we think now are the right transitions would work the same way and have the same selection rules. So this is the basic thinking for vanilla Fleischmann Pons. Now,
just to understand, the A star, the receiver was the A star transition to A. So the deuteron in the excited state and the deuteron in, let's say, not the excited state.
But if you like, the deuteron has a ground state, and if you have an A matrix element and you go to a positive energy state, there's a localized positive energy state, which is a candidate, which seemed to us to be our best shot at a state in a transition. And we calculated that out, and there's perfectly good transition. You can carry through the calculation. You can execute everything given the approximations that are normally made in nuclear physics, and you can get an answer out. Today I look back at that and look at the number and say, well, that's too small to do the job. I need a bigger coupling, I need stronger coupling. Well, it turns out that the excited positive energy state that we looked at is one transition. There are other transitions as well. Some of the other transitions have much stronger coupling. And those other transitions which have much stronger coupling would have coupling matrix elements that should be big enough to do the job. So that, and we've got to go redo the analysis and calculate things out. So hopefully this year sometime we're going to come back and try to beat that problem up some more. So in the single laser experiments, so these experiments, if you like, they're a little bit different. We got a 2-volt red laser coming in the surface. We saw that it turned the heat on, it turned the heat off. The donor reaction D2 to helium-4, so the excitation that's coming in is like 2 volts or thereabouts. So there's no vibrational nodes at 2 volts, but there are surface plasmon nodes. But the surface plasmon nodes have some non-trivial coupling with the optical phonon nodes. So the thinking here is that the hybrid plasmon optical phonon mode, so the plasmon's moving, the lighter nuclei are moving along with it, a small amount. But a small amount's actually good enough. And so this would be the oscillator in this case, and the light nuclei they're moving are the deuterons, so once again the deuterons would be the receiver. Only in this case, instead of being an optical phonon mode, it would be the plasmon optical phonon mode hybrid that would be oscillating. Let's consider another example. In experiments, the cryogenic experiments at SRI, some experiments were done with light water in palladium, and excess energy was observed. There are other examples. There are not as many, but for many years, light water in palladium was thought to be inert, and was used as a control experiment. There are experiments now which suggest that it is possible to get excess heat from light water.
Ordinary water or light water?
Ordinary water. When I say light water, I'm meaning ordinary water. So the thought here is that instead of DD going to helium-4, it's HD going to helium-3. And in this case, if you follow the same arguments, well, if again, we don't have a two-laser experiment for a light water palladium experiment. We don't have this, we don't have that. So we're in a region where this is more speculative and conjecture. But the thinking is that if you have optical phonon mode excitation, you've got HD to helium-3 transition to get the energy. The question is what's the receiver? Well, you got deuterons, you got protons, you got many more protons than deuterons. So the thinking is that the proton has the possibility of being a receiver in this configuration. And at this point, I'm looking forward to calculating out the proton as a possible receiver to see what the strength is.
So as well as ED reaction, there's the also HD reaction, which may or probably happen.
Yeah, it would be consistent with everything else that we've thought about and described so far. So I'm looking at it as a serious candidate.
Is there any incident helium-3 or helium-3 was found?
As I will emphasize shortly, there are no experiments where helium-3 has been seen in the gas phase. On the other hand, there's no experiments with a normal light water contaminated with deuterium that's shown excess heat that's been put in front of a helium-3 detector. We had funding lined up to do that with a Piantelli experiment at one point, and then it was found to be inconsistent with the wishes of the folks involved in the energy initiative at MIT, so it was canceled. So the chance to get exactly that measurement, which would have been an incredibly important measurement, didn't happen. There's no resources to get it done. Okay, there are hot spots observed in some cases in palladium deuteride experiments. In this case, the thought being that associated with the hot spots, perhaps we've got compressional acoustic modes being the excited mode. And the donor reaction would be D2 to helium-4 again, but this time instead of deuterons or protons being a receiver, if you've got acoustic mode, well, the palladium is moving. And palladium is doing a lot of moving, it has most of the energy. So in this case, the proposed receiver would be the palladium nucleon. So there are hot spots. If the palladium is being involved for receiver duties, then there's going to be the possibility of internal energy in the palladium. And there are transitions to positive states, some of which can dissociate or disintegrate. And in connection with this, there's been observed for years elemental anomalies. So within this particular scheme, if you've got acoustical mode operation, then your host lattice is going to be involved as a receiver. Those are conditions under which you have the possibility of getting acoustical anomalies. If you're trying to make a excess heat, commercial excess heat system, probably having your host metal disintegrate might not be the optimum thing that you want to do. In the case of palladium disintegration, palladium is very exothermic. And I'm thinking that that's why the hot spots are hot, because you get a boost from the palladium disintegration. Palladium's very expensive. You'd like not to disintegrate the palladium.
So in this experiment, the frequency can be also lower than 1 terahertz. So because all the acoustic modes are
acoustic modes in palladium deuteride go up to 5+ terahertz. There's not been any studies that I'm familiar with showing excess heat as a function of acoustical mode excitation in a Fleischmann Pons cell. But in this particular case, if there were some generic experiment where you could tune it back and forth, I would expect the optical phonon mode excitation to lead to clean excess heat without much disintegration, and then tune down and drive it in the acoustical mode range. I would expect that you start to see disintegration of the host metal lattice. Okay, nickel hydrogen. So, although we haven't quite gotten to it, and we'll get to it shortly, excess heat has been observed in the light water nickel hydrogen system, where light water, when I use the phrase light water, means deuterium contamination. So in this case, in the case of nickel, the solubility, we're going to talk more about this, but the solubility of H isn't very good. So you have problems getting an optical phonon mode that's delocalized in the first place. So the thinking is that HD going to helium-3 is the source of the energy. Receiver is going to be nickel nuclei in the absence of an optical phonon mode. And I'm of the opinion that the Piantelli experiment and some of the nickel hydrogen powder experiments work this way. Now, you can load nickel hydrogen electrochemically. You can load it actually high enough to get an optical phonon mode. So I'm actually of the opinion that electrochemical nickel hydrogen, nickel hydride experiments probably are optical phonon mode experiments, in which case they wouldn't have the issue with respect to the transmutation.
So would you expect that if we actually did an experiment like this with 100% pure light water, with no deuterium at all, that we wouldn't see anything?
That would be a possibility. Now, there's one experiment that's been reported that claims to be exactly that. Bush and Eagleton, years and years and years ago, worked with light water under conditions where they said there was no deuterium in the system at all. They ran it, they saw perfectly fine excess heat. So I'm looking at that experiment, I'm scratching my head. So it is an experiment which, if I accept, blows a hole through the conjecture. But we'll talk a little bit more about that.
Whose work was that?
Bush and Eagleton.
Or to follow on from that, if we've got low concentrations of deuterium, to first order, if this is true, wouldn't we, like, we double the concentration of deuterium, expect to see about twice the output?
See, what's the phrase? Great minds grovel in similar gutters, or something. The same thought occurred to me and to Mitch. I'll talk a little bit about some results from that. My response to this is that why don't we hook up a helium-3 detector next to a nickel hydrogen experiment and see if we get helium-3. The Celani experiment. So in Celani's experiment, he's working with a nickel alloy. And in his nickel alloy, he gets much higher solubility of hydrogen. So in this case, HD to helium-3, I'm proposing is the donor reaction. Now, if you've got high solubility, you have the chance of having an optical phonon mode. So in this case, H or D nuclei would be the receiver. And compressional optical phonon modes for the oscillator. So I'm of the opinion that Celani's experiment is an incredibly important experiment, because if you've got a rather cheap nickel alloy with high hydrogen solubility, of course, there are issues. He processes it in order to get nanostructure internally, so it's not just a piece of constantine. Okay, so takeaway message. So we have donor and receiver schemes for excess heat. Not just one, there's quite a few of them. I think that there's two primary donor transitions for the excess heat, D2 to helium-4, HD going to helium-3. There are other possibilities as well. You could have T and H going to helium-4. Of course, working with T is problematic because you don't really want to have a lot of tritium in your laboratory and so forth. In terms of tritium production, if you've got D2 going to an HT molecule, that would be a natural way to extend the scheme for stationary tritium production. You would expect, if you're making a molecule, that the maximum rate for tritium production would be orders of magnitude down for helium-4, and that sort of is not inconsistent with experimental observations. We have no experimental evidence at present for helium-3 as a product, and that's just got to be number one on my wish list for further experimentation for nickel hydrogen. Expect light nuclei as receivers for optical phonon mode operation, and light nuclei as receivers my view is sort of clean. Expect heavy nucleus receivers for acoustical mode operation. And heavy nuclei have internal transitions of positive energy states which are potentially accessible, which leads to loss of your primary energy that you're making and destruction of your host metal. And that's bad in my view. Oh, takeaway message, questions, comments, thoughts?
I know that Lossy claimed that nickel can transmute it in copper, and to find some support to his hypothesis, he told that the ratio of isotopes in such copper in the resulting piece after the reaction takes place is different than natural occurrence.
I'm not going to comment. I'm familiar with those claims. I'm not going to comment on them here. However, I will talk about the problem shortly. I'll present some observations.
This is a general question, but is it easy to distinguish between, as a mass free gas, between HD and helium-3?
So a few days ago, I showed the mass spectroscopy showing the D2 line and showing the helium-4 line, which a good mass spectrometer is able to separate. Turns out HD and helium-3 are much closer together, so you actually need a much better mass spectrometer. And you have to really worry about the separation of the HD. You have to remove a lot of HD to get the helium-3 line to, you know, so one doesn't swamp the other, so you can't see them. Other question?
Peter, just to be clear, you don't think there's any HH reaction?
Well, there's of course an HH reaction that, if you like, two H's that go to helium-2, but helium-2 is unstable, so you possibility of a P plus a beta decay reaction to get you to deuteron, which is what's thought to happen in the sun for proton burning. The only issue is that because a weak interaction decay process is involved, there's no possibility of having a coherent, I don't think there's a possibility of having a coherent version, so I don't think you can get P plus P making a deuteron associated with this kind of scheme. You have to go through and analyze and double check all the fine print everywhere, but at the moment I don't think that's consistent with the scheme.
This may be a silly question because I'm not familiar with condensed matter physics in general, but the coupling mechanism that you're talking about in the Lossy spin-boson model, is the coupling mechanism some large number of photons between
no,
nuclear...
the coupling mechanism, the A dot CP interaction is one that says exchange one phonon and raise or lower a nuclear transition. That's all there is to it. So it's only one phonon quantum at a time, but as we recognize, the Lossy spin-boson model does a fractionation or inverse fractionation by having many of these things happen while coherence is maintained. So you can have a large number of quanta by many sequential coherent single quanta events.
There's no photon in the mix between...
well, there is a photon emission matrix element, but the proposal here within the Lossy spin-boson type models, the models I'm talking about, is all of the interactions going on with a highly excited vibrational mode, so it's all phonon exchange.
So it just goes directly from
yeah.
to the phonon.
Yeah.
It was reported that the nickel does not work with deuterium in some reports. So why in your model there is deuterium is required? So
okay, there are some experiments. For example, the SRI cryogenic experiments where deuterium was run in nickel, and the results were not terribly different from deuterium in palladium. So from my perspective, deuterium is in this scheme is happy in a nickel lattice and D2 formation and near vacancy. All that should work similarly. I think there are issues. with respect to low solubility. So if you have acoustic mode operation, you put your energy in the nickel, you disintegrates in your nickel, so your lattice has problems. So you might expect degradation of the lattice itself. So there may be other material science related reasons that might have to do with the difficulties involved. I mean, Piantelli sees excess heat from nickel deuterium, but it's a much smaller level than for nickel hydrogen, for example.
In one of your slides, you proposed that the nucleus of the palladium might be the receiver. And I understand that that depends to some extent on the mass of the nucleus. Is that right?
Well, basically, at this point, you have equations, you have the model, you look at it, and transitions to negative energy states look like they're by far the strongest transitions. So all nuclei can have such transitions. The big issue is that if you have a heavy nucleus, you've got a very large number of positive energy states which have coupling to it. So if you like, that's bad. The simpler, lighter nuclei have much less of that. So if you like, the headache is giving a nucleus energy in degrees of freedom where it can blow the nucleus up.
What I'm leading up to is if you used a nucleus that was lighter, because you have an isotope with less neutrons, would that type of experiment
Yeah, at the moment, my models wouldn't be thrilled. I mean, for example, you can imagine having palladium nuclei focusing on palladium 102 rather than palladium 104, 105, 106, 108, 110, and that would have fewer neutrons. But I don't know that my model's going to care a lot about that one way or another. Okay, let's think a little bit about maximum reaction rate within the model. So the donor-receiver model, basically it says if the receiver can't fractionate, no reactions happen. If the receiver can fractionate really well, then excess heat is limited by the donor transition. And in that case, you can figure out you can get a simple formula for the maximum reaction rate. And the simple formula in general is this. So you get this is the piece that says that if the donors were matched to the oscillator perfectly and could give the energy up, this would be how fast things would go. Here's the Coulomb repulsion, the tunneling factor due to Coulomb repulsion. This is the Dickey factor, which basically says if you've got more of the donors around, that's a good thing, things happen faster. It happens in a Dickey sense, which basically says that if the reaction's been going on for a while, then it's going to work better. And then you get the hindrance factor due to the receiver, which we talked a little bit about previously. So the question is if you plug in numbers, what do you get? Well, in order to plug in numbers, you need a calculation of the DD to helium-4 matrix element. And as I remarked, an effort was made to just calculate this out by brute force. And so we took the matrix element, we did a lot of algebra and numerical calculations, and in the end we get an expression that looks like this. So it's a prefactor, there's a CP, so this gives you a single phonon exchange. There's the Coulomb tunneling factor, and this basically says that if it looks like if it's the size of a nucleus of a molecule in vacuum, then these factors are 1, but if the being in the metal makes it bigger, it makes it smaller, then you've got corrections to it. Also, it basically says that get the triplet P, L equals 1. The selection rules actually want to have 1 unit of angular momentum in the D2 initially. So there are selection rules associated with this. Another issue is that if you have compressional modes, the compressional modes, if you like, squash the molecule, the D's get to be a little bit closer together, then the tunneling factor is going to be a very strong function. So you can have possibly a phonon exchange associated with the tunneling matrix element on top of everything else. I actually think that's a big issue. So excitation of compressional optical phonon modes are seen to be effective at exoseed production. That's the LETS experiment and the one laser, two laser experiments. You wonder why, and one issue is that from the models you would expect X-ray emission or emission of other things connected to vibrations not to care whether you got compressional modes or transverse modes. There's nothing in the theory that says you should care one way or another. But compressional optical phonon mode may have an advantage because maybe you got some compression, local compression of the Deuteron, and a little bit of local compression translates into a lot of gamma factor changes. So I think that's why compressional modes are favored in the experiments. Thinking about the model, so we have a rate formula. The rate formula, the cool thing about the rate formula is it's understandable. In fact, before we had a model, I was writing down rate formula that had the various terms sort of like that. No reactions at the receiver, can't subdivide, fractionate the model. The hindrance factor associated with the receiver is a big deal. Basically, if you don't make up conditions where fractionation occurs, nothing's going to happen. So for example, if your vibrational mode's not highly excited, according to the model, you're not going to get any reactions, period. Thermally, you're not going to get anything. You have to have a highly excited vibrational mode to get things going. If you think about it, if you look at the experimental results for XOC as a function of current density, there's nothing, and then it turns on and goes up linearly. So this is sort of saying that if you believe that the current density gives you deuterium flux makes optical phonon mode excitation, nothing happens at all until your optical phonon excitation gets to be big enough. And the threshold, it's big enough, and then reactions can proceed. So a curve flat, then going up, is the kind of thing you would expect from the associated hindrance factor. Next biggest issue is the gamma factor for tunneling through Coulomb barrier. Finally, having more D2 is good, and Dickey factor increases the reaction, which basically means, according to this, there's going to be some history. There's going to be some dynamics beyond just the simple reaction rate stuff. And numerically, the maximum reaction rate from the model calculates out to be consistent with the experiment.
How does magnetism factor into the rate factor?
I'd argued earlier that in the specific case of deuterium, which is the one we've analyzed, the matrix element associated with being a receiver has spin selection rules. So basically it can couple to 2 of the nuclear spins out of 3 possible. So you've only got 2/3 of the receivers doing anything. If you add magnetization, you can change the nuclear spin population. It turns out in the model the ability of the receiver to fractionate quantum is exponential in terms of the number of receiver nuclei you have. So if you put in magnetization, you can get nuclear spin polarization. You have the possibility of increasing the rates. So if you're at a low hindrance factor and you double the number of nuclei participating, you're going to get a gigantic increase in the ability of the system to fractionate, and you're going to see a large impact from a magnetic field. And by the way, the selection rules, like I say, seem to be consistent with the experimental observations.
I'm trying to get a physical picture of the coupling to the phonon mode. I'm wondering what sort of volume would be necessary to not just have the local material kind of vaporize with 24 MeV if you're coupling to the phonon.
Well, in my view, if you've got a localized phonon mode, you're not going to do anything. You can't have enough nuclei coupled to it to make anything work. You have to have a delocalized phonon mode. Right. So you have to have something big vibrating. You have to have coherence in the vibrations over a large...
How large are we talking in terms of...
In the LETS experiment, there's this dynamics. The laser turns on, the excess heat wanders up, and depending on which frequency difference he hits it takes different times to wander up. And I'm scratching my head, I'm thinking, well, laser is focusing down a millimeter, the thing's a centimeter. I'm actually thinking that what's going on is it starts out sort of doing its thing on a small scale, and then it spreads out, and eventually the whole thing's going. I think it's a little bit like a laser mode, that wherever coherent vibrations can be induced, they're going to be induced, the bigger the better, and the model likes more.
So couldn't there be issues getting down to the real nanomaterials that Mitchell was working on? Like if the volume is just really too small to hold.
Well,
that.
again, in the nanomaterials, depending on how many of the resins you have and how far separated the vibrations have the possibility of talking to each other at the different. I mean, that's a big issue. And one of these days, I want to see Mitchell do experiments with high density of his resins and then lower density of the resins, because at some point, if that picture is right, if they're too far away and you can't have a vibrational coupling, then it shouldn't be able to do its duty. I'm going to run out of time. Let me think back. We talked on the first day about Heisenga's 3 miracles, and I'm going to make this 3 miracles plus. I'm going to correct Heisenga. So we have the fusion rate miracle. How do we overcome the Coulomb barrier? Well, in this model, we don't overcome the Coulomb barrier. What we do is we have it only come in once rather than twice, and we pick up lots of orders of magnitude and reaction rate by doing it. So in this kind of scenario, we are happy with the Coulomb barrier. No special work to try to make it go away. Branching ratio miracle. So if you get 2 deuterons close together and you have an incoherent process, you've got the 3 + 1 as the primary branching ratios. So how do you do that? How do you muck with the microscopic physics for an incoherent fusion reaction? My answer is you don't. You can't. That's impossible. Everybody knows that's impossible. The only issue is that because an incoherent reaction process has E-2G, it's down by a gazillion orders of magnitude. So this basically isn't going to happen, and in the experiments it's observed not to happen, so we're happy. Number 3, Heisenga had a concealed product miracle focusing on the 24 MeV gamma and crossing that out and say, well, it's much bigger than that. It has to do with anything energetic coming out commensurate. And if you take your big quantum and you subdivide it and fractionate it in lots of small quanta, then the energy is going into other degrees of freedom. So there's no more miracle. There's a natural explanation for it. Number 4, which Heisenga didn't include but should have, is that excess heat of Fleischmann Pons is just simply inconsistent with condensed matter nuclear physics, and we need a rewrite of both starting at the beginning. Okay, so we've rolled up our sleeves, and all we did is we had a better starting point and found some fine print and warranty for the generalized foldable Tuzin, and we've got some version of condensed matter nuclear physics which seems to be quite relevant to the problem. All right, comments, thoughts, questions?
Yeah, I think you focused a lot on how to get rid of the energy.
Which I think is the biggest problem of all.
I'm not sure I understood the response to number 1 and 2.
Okay, number 1, how can you overcome the Coulomb barrier? So 1989, 1990, a number of physicists, Kuhnen and Nauenberg and lots of others, had focused on the D2 molecule problem, which we talked about on day 1. And they said, we can analyze this, the fusion rate is terribly slow, it's on the order of 10 to the minus 64 seconds per molecule. And they said because that's small, they next said that you would expect D2 fusion in palladium deuteride to sort of work the same way and have a similarly slow rate. Now, that argument, as we'll see shortly, is wrong by more than 10 orders of magnitude. But let's accept it anyway. So the argument is, given the situation, given the slow rate for fusion in the molecule, how do you ever get 2 deuterons together? And the answer is for an incoherent process, you can't ever get 2 deuterons together enough to do anything useful whatsoever. It's not a relevant model. On the other hand, these new models are coherent. And since they're coherent, the formula for the reaction rate depends on the Coulomb barrier differently. So it only comes in once instead of twice. Since it only comes in once, we're facing e to the minus g. So it's almost as if you pick up all the 35 orders of magnitude you lose in the molecule for an incoherent process. For the extra e to the minus g, you get back for the coherent rate. So that's the argument. So we're not doing anything special to overcome the Coulomb barrier. What we're doing is we're saying that this is a big problem if you have an incoherent process. But if you have a coherent process, then it's not an issue. It's just simply not that big of an issue. It remains an issue, as we'll talk about shortly, but it's nowhere near as big of an issue. So
So the coherence is the key there. And then for the number 2?
For number 2, if you have an incoherent fusion reaction, then 2 plus 2 goes to 3 plus 1, 50-50 roughly. And Huizenga's saying, okay, you don't see 50-50, show me how in an incoherent reaction you deviate from 50-50, knowing full well that the answer is there's no way you can do that at all. That's hopeless. And my answer is that let's not try to change the 2 plus 2 going to 3 plus 1 branching ratio for the incoherent reaction. Let's keep it. We're happy with incoherent reactions. They don't happen. So we're going to maintain the 50-50 branching ratio in the incoherent pathways because there's nothing you can do about it. And the only thing is the coherent reaction that's under discussion is a separate coherent pathway. So it has its own rules and study its rules. And it favors helium-4 and it doesn't favor 3 plus 1. 3 plus 1 would require molecular formation, so they're going to be inhibited by orders of magnitude because you've got a molecule rather than a single nucleus.
So, in your view, there is no triggering of the reaction due to bombardment of, let's say, muons or other particles. So,
I'm not going to say exactly that. There's evidence that you can get big effects if you bombard with fast electrons or gammas. We'll talk about that shortly. Okay, let's talk about screening. Yeah. So why are we interested in screening? Well, we're interested in screening for the following reason. We've seen that the coherent reaction rate is linear in the gamma factor. And incoherent reaction rates are quadratic in the gamma factor. Now the coherent business provides us a mechanism for quote unquote getting around the Coulomb barrier, except that you can't get around the Coulomb barrier. We're happy with the Coulomb barrier. It's just less of an issue if it's only showing up once, but it's still there once. And because it's still there once, we have to worry about screening. So screening makes a huge difference even if you're only linear in the gamma factor. That motivates us to consider screening effects. And that drives us to consider low energy beam experiments. So this problem's been studied for a lot of different reasons and why there's a very good nuclear physicist, Klaus Rolf, who's been interested in the problem for years. And he had a group that studied it, and then his students went on and collaborators went on and studied it. So here's an example of low energy deuteron beam experiment. Electron cyclotron resonance source deuterons come through. They hit a target which is deuterated, and then they have detectors to look for fusion, DD fusion products. And what you see is, for example, in aluminum, so here's the energy. Here's 2 kilovolts, 5 kilovolts, 10 kilovolts, 15 kilovolts. So these are low energy deuteron beam reactions. In the case of aluminum, there's the deuterium in the beam comes in, it plants itself in the aluminum. Another deuteron comes along, and you get a fusion reaction. And in this particular case, it's plotted in terms of the S factor. And the S factor is flat if there's no screening effects. Basically, you take the cross-section, you take out all the obvious energy dependence. Whatever is not obvious that's left is what you're looking for. So in the case of aluminum, the screening energy is 30 volts. The screening energy is defined sort of this way. You start out with an underlying picture for Coulomb repulsion that's exponentially screened. And there's a distance, characteristic distance for your screening. And then the energy is going to E squared over your characteristic distance. So for example, if your screening length is 1 Bohr radius, 0.529 angstroms, then E squared over the Bohr radius is going to be 2 by h, or 2 times 13.6 electron volts, 27 electron volts. So what we see is that if 2 deuterons were brought together, you would kind of expect the screening energy to be about 27 volts. So in aluminum, the number is less than 30 volts, which is consistent with no screening effect whatsoever. In palladium, what you see is a low energy. You get an increase in the astrophysical S factor. And in this particular experiment, the screening energy is consistent with 800 electron volts, which means the screening length is ridiculously small. And this is interpreted as being experimental observation of large screening. Now, over the years, there's been experiments done on lots of different metals. So this is Z, going from 0 to 90. This is the screening energy in electron volts. So here's 0, 200, 400, 600, 800. So if we go to 46 on our dial, there's a lot of experiments, a lot of different energies. The highest ones are near 800, which is consistent with the data that I showed you. Folks in the literature kind of think that, well, there's more experimental data points around 400, so the screening energy ought to be closer to 400. The theory, if you do Thomas Fermi screening, there's some calculations that show that you'd expect the screening energy to be close to 130 electron volts, which would be sort of down here. If you look elsewhere, if we look at nickel, nickel's here. Nickel's got screening sort of a little bit like palladium. There's other guys that screen as well. These points are for the loading that was achieved in the experiments. So screening occurs. It's a big effect. The screening impacts the incoherent fusion rate. So these curves are well known. If you have if you have screening for the molecule, the calculated rate is somewhere right about here. So this curve, which looks like it's hitting the line here, you should imagine it goes all the way down to about here. Now, if you have a screening energy of, say, 400 volts, then your incoherent reaction rate goes from 10 to the minus 65 up to, I don't know, 10 to the minus 10th or 13th or 14th or something. So that's good for like 50 orders of magnitude. So some people have said that the low-level fusion effect seen by Jones is due to screening. Now there's experimental evidence in low-energy beam experiments for there being a lot of screening. So they're saying, well, maybe the experiments, low-energy emission could be explained by that. I'm very skeptical of that, mostly because Baranowski did some diamond anvil loading experiments. We put a lot of deuterium into palladium, had a neutron detector in, didn't see diddly squat. And if you actually had screening of this magnitude in real life, then he should have seen neutrons coming out, but there weren't neutrons coming out. But what this argues is that from the beam experiments, we know that there is screening showing up. You might say, well, maybe the kinetic experiment's a little bit different than the static experiment. The deuteron comes in, hits another one. Maybe when they fuse, they move. Maybe they go into outer orbitals of the nearby metal atom, and maybe that gives you more screening. But the Thomas Fermi screening numbers, those are substantial, and those you would expect in the static situation. So we recall on day one, we calculated the screening for the D2 molecule and penetration. This is 10 to the minus 40th, and this is near 1, so you might look at that and say, well, you get 40 orders of magnitude, but there's a radial factor because this is P instead of R, so it's actually 10 to the minus 35. So this is basically, the molecule is basically consistent with the 10 to the minus 35 screening number, 10 to the minus 35 tunneling number, but if you have screening, you're going to get more penetration. So conclusion from the beam experiments, very large screening effects are seen. They're seen in metal targets, but not in insulators, also not in semiconductors. Rolfs interprets this in terms of device screening, but I kind of think that there are two issues. One, Thomas Fermi, or more accurate, many-body electron screening models would be more relevant for the static problem. The dynamic problem, I don't actually think I've seen a calculation of the dynamic problem yet. I think the dynamic problem really has to be solved to understand these screening experiments. So somewhere between 200 and 800 from the beam experiments. the Thomas Fermi number in Schirsky 2004 is 133.8 electron volts, and also large screening seen in nickel. Ed Storms has been interested for years in where the reactions happen. He's got something called the nuclear active environment. And after some encouragement, Storms has recently specified exactly where he thinks the nuclear active environment is. And there's a paper that discusses this a lot. In essence, his proposal is that if you have small voids or cracks, then you get deuterium formation or hydrogen formation in these voids or cracks. Now, he's been encouraging me for a while to forget about this monovacancy business and look at the voids and cracks. So if I look at the voids and cracks, well, I can actually know quite a bit about voids and cracks. So Storms thinks that the active region are these small voids and small cracks. And I'm thinking that the electron density, the background electron density drops down very quickly away from the metal atoms. So all I have to do is be like, I don't know, half an angstrom out of position next to a metal atom, and your molecule becomes a molecule. It doesn't become a sigma bonded dihydrogen complex with a little bit of separation. So, so if your molecule looks like a molecule and it's away from the metal, you've got no screening, which means you would expect to see the molecular screening number. You'd expect to see 25, 27 volts for the screening energy in this case. And in this particular case, then, because you don't get the metal screening away from the surfaces in these small voids or cracks, you're giving up more than 10 orders of magnitude in the gamma factor using this approach. So I'm of the opinion that you really do want and need the high electron density and having the metal atoms be nearby to do your screening.
I don't have a very good intuition for the screening energy that you're talking about, what that means. Could you relate that to reaction cross-section? Is it in some way?
Sure. I mean, we saw pictures of it. For example, for the astrophysical S factors, you go down in energy, you basically get the standard number. I think it's, in these units, I think it's like 50 or 70 or something like that. And then if your screening number is 800 volts, what happens is that here you're getting bigger and bigger and bigger, and this is up at a few keV. And by the time you get down to small numbers, this is like orders and orders of magnitude. So basically the orders of magnitude we saw in the other plot, this is just extending that curve down to low energy. So basically the good way to think about it is here's the screening energy and here's the change in tunneling for the D2 molecule kind of problem. Not change in tunneling, change in rate, which depends on e to the minus g squared. Okay, so takeaway message. Big screening observed in experiments. Expect not quite as big screening from theory, but that's not really right. That's apples and oranges. Thomas Fermi gives lower screening for the static problem, but the beam problem is the dynamic problem. And the dynamic problem, again, I haven't seen the papers yet where that's been analyzed in detail with modern models. Makes orders of magnitude impact on gamma factor. We want to take advantage of maximum screening to get maximum reaction rate. D2 and cracks and voids wouldn't see it, but D2 in a monovacancy should see the screening because we're getting the D2 molecular form where there's some non-trivial amount of electron density. And we got nearby outer orbitals in metal. Catch my breath. Questions? Comments? Okay. What about nickel hydrogen? I promised I was going to talk about nickel hydrogen on Friday. According to my watch, it's Friday. So, before looking at the detailed experimental results, excess heat is seen in nickel hydrogen experiments. The effect was discovered in the case of electrochemical experiment by Randall Mills and collaborator Knisis. excess heat in gas loading experiments was published in 1994. The discovery was sometime earlier. A big issue is that nickel hydrogen is not palladium deuteride, as we're gonna see. We have to think about the problem somewhat differently. I mean, nice thing about palladium deuteride is we got a reference problem where a lot of work's gone on, we got a lot of analysis, we got some intuition. Now we'd like to think about nickel hydrogen. Sadly, we're not going to be able to use all of our same intuition. We'll be able to use some of our same intuition. Differences are important. The nickel hydrogen lattice structure looks like this. As we can see, this is different from the palladium deuteride lattice structure because now there's nickel atoms here instead of palladium atoms, and there's hydrogen here instead of deuterium atoms. And it's a little bit smaller. This part's nice. Now, we recalled our arguments about background electron density, and the background electron density in the case of nickel is higher. So we recall that according to embedded atom theory, at least in one calculation, the hydrogen was looking for 0.069 electrons per cubic angstroms, which are down here. And what you get at the O site is up there. So you'd expect O site occupation, which is observed, but because there's so much energy difference here, we conclude that the solubility is going to be down. So we take our intuition, at some point we go to experiment, and here's the experiment. Now, even this phase diagram sort of looks qualitatively familiar. These are the isotherms, low loading, they go up, the pressure isotherm, or the isotherm as a function of pressure here goes over here, it's flat, there's a miscibility gap, sort of just like there was for palladium hydride, palladium deuteride. The only thing is that instead of having the curve, this is 25C, somewhere near above room temperature in January in Massachusetts. We have lines going back and forth, but the pressure, instead of being less than 1/10 of an atmosphere, is 400 megapascals. And I screwed up the number before. 1 atmosphere is on the order of 100,000 megapascals. So this 400 megapascal number is close to 4,000 atmospheres. So in order to get across the miscibility gap, you got to do some work. Let's think about this as compared with the equivalent palladium deuteride curve. So here's 1/10 of an atmosphere, below 1/10 of an atmosphere. So you can load to the miscibility gap in palladium deuteride at relatively low number of atmospheres. You want to get across the miscibility gap in nickel hydride near room temperature, you got to go to 400. You're way up here. So if you think about it, to get loading across the miscibility gap in nickel hydride, you have to have electrochemical loading, which is equivalent to being incredibly heroic in palladium hydride, palladium deuteride. You can load it, but it's not easy. So this is what we just argued. Now, when you do load, hydrogen in nickel works differently than hydrogen in palladium. So in hydrogen palladium at low loading, the hydrogen is randomly spaced. And as the loading gets higher, the loading is either randomly spaced or there's some other phase, perhaps the other phase involves hydrogen-hydrogen correlations. In nickel, what you see is that when you do X-ray observations, if you have loading in the miscibility gap region, you don't see lattice constant that would correspond to the miscibility gap loading. What you see is either nickel with no hydrogen, or you see lattice constant corresponding with the hydrogen at high loading. So, for example, how do you explain this? Suppose you have nickel hydrogen loaded to 10%. You do your X-ray measurement. Most of the nickel looks like it has no hydrogen. Some of the nickel looks like it's loaded to 0.7. What's the answer? Clumping. The hydrogen likes each other in nickel, so it clumps together. You put in a little bit of hydrogen, it segregates. There's some here, there'll be clump here, but mostly everywhere there's no hydrogen. You've just got bare nickel. this is qualitatively different than how things work in palladium hydride. I submit this is important, and it's cool. So hydrogen clusters in nickel. Thought that hydrogen probably clusters in palladium hydride, but it's a weaker effect. For example, there's a conjecture that you can understand quantitatively the two-phase region immiscibility gap on palladium hydride by saying your two phases, one is random hydrogen, the other is hydrogen pseudomolecules. First example of clumping. Now, we were interested in vacancy formation, and we said at palladium deuteride, palladium hydride, you have to be loading at 0.95 to get your vacancy stabilized. Well, in nickel, you don't have to go up as high, and if clumping gives you 0.7, wherever you clump, you put in hydrogen into nickel, it clumps, and it clumps at a density, local density, sufficiently high to stabilize vacancy formation. Sure, we're definitely not in palladium anymore. This does not happen in palladium. So H clusters in nickel, there's not an intermediate loading phase observed in lattice constant measurements. And the loading that's observed is a loading sufficiently high to exceed the vacancy stabilization threshold. So we would expect Foucault phase generation in nickel hydride if you can have the vacancies move. I mean, if you like, the whole game in Fleischmann Pons experiment, as we were arguing before, was to make Foucault phase vacancies, which we did high loading and co-deposition. Well, in nickel, all you got to do is put in a little bit of hydrogen clusters to exceed the vacancy stabilization threshold. Now all you got to do is arrange conditions so that the the vacancies can move. And if you can, you'll get natural formation of Foucault phase structure. Now we recall that Foucault phase structure takes the host metal nuclei and in an ordered fashion replaces them with vacancies. So this is the kind of thing that we're talking about for nickel hydride. And we argued that the nice thing about the vacancy is that around a vacancy, and this is palladium deuteride, around a vacancy you've got the possibility of getting the electron density to be sufficiently low to get a molecule. In nickel hydride, or in nickel around a vacancy, you also have electron density sufficiently low that you have the possibility of molecular H2 or HD formation or D2 formation. So that part of the problem is very similar. So the takeaway message: nickel is hard to load, it clusters, you exceed the loading density for vacancy stabilization once you cluster at all. You'd expect Foucault phase if you can if you can diffuse from internal surfaces. You probably like elevated temperature in our nickel hydride system in order to encourage vacancy diffusion. And if excess heat in palladium is due to D2 formation near amount of vacancies, in palladium, density functional calculations have been done for a similar amount of vacancy system in nickel. It's basically the kid's sister, the local environment. The arguments are almost identical. Now, it brings us to the Piantelli experiment. Takeaway message. Let me be fair and honest. Anybody have questions or thoughts or comments? Okay. Piantelli experiment. In my view, Piantelli experiment's sort of a fundamental experiment for understanding what's going on in the high temperature nickel hydrogen gas experiments. So here's the experiment. Piantelli in the early days worked with a nickel rod. So here's the specs for this one: 9 centimeters length, half a centimeter in diameter. So this experiment's not nickel powder, nano nickel, or anything. It's just a nickel rod. And it's not just a nickel rod. One of my friends worked from Piantelli's paper to try to replicate it. Nothing happened whatsoever. And he said, "What's wrong?" Well, there's some surface processing that's like really critical. It has to be done, and the experiment doesn't work without it. And that somehow didn't manage to get documented in those papers, sadly. So here's calibration. There's no gas. The temperature goes up when you put in heater power. If there's gas in, then you get a calibration curve. So what you'd like to do is you'd like to see higher temperature for a given input power to see if there's excess heat present. So here's some of the first data showing excess heat. In this particular experiment, the input powers, I was estimating from the paper 140 watts. One of my friends read the paper more carefully and said, yes, it is 140 watts, and the excess power is 20 watts. So, like nickel's a little bit cheaper than palladium, bigger systems, bigger effects, bigger everything. Here's an example of temperature as a function of heater power. So this is when there's no excess heat going on. Here's what 20 watts of excess heat looks like. Here's what 40 watts of excess heat looks like in these early experiments. Here's a cross-section of their experiment in the 1998 paper. I think the rod is here. I guess it's a pipe. It looks like a pipe here. Again, I haven't read this paper for a while, so I'm a little bit rusty. What I wanted to draw your attention to was here's TC4, here's TC1, TC2, TC3. There's different temperature sensors. So TC4 is farthest away from the rod. Where's the other one? TC1 is pretty close. This measurement is pretty close to the rod. So here's what the calibration looks like. TC4, which is away, you heat up. There, in the sample, there was a platinum heater. These guys right here, it's a platinum heater wrapped around, so you have to heat it up to get things to go. So what you see is that T1's closest to the sample, it's hottest, T4 is furthest away, it's much colder, so there's this giant temperature gradient in the system. According to some of the early discussion on this, that temperature gradient is a key feature of the experiment. When you do an experiment, you like to have isothermal conditions, and apparently this thing doesn't work with isothermal conditions. So the basic observation, the basic claim, if you like, is that you're running the thing in power balance. You go, in this case, through a temperature cycle, and when you're done with the temperature cycle, the temperature's higher, which basically, between here and here, you're seeing that the temperature's higher because the nickel hydride is now producing excess power. So we talked about the pressure composition isotherms, and if you look in the literature and you say, well, how much loading do you expect at the temperatures that are under discussion? Near 1 atmosphere, you don't expect much loading. So this is loading in units of 10 to the minus 3. Here's 1 in units of 10 to the minus 3. And here's numbers which are a small fraction of 10 to the minus 3. So you'd expect bulk loading in nickel to be very low. On the other hand, if you look at their experimental data, a good way to figure out how much loading you have is to measure the hydrogen gas pressure in the cell. So for example, in experiments we did at MIT would load a volume up with hydrogen gas or deuterium gas, and heat the sample up to burn off the oxide layer. Once the oxide layer is burned off, then you get to see the pressure go down. It drops like a rock while the metal absorbs all the hydrogen and deuterium. Here we're seeing going from over 1,000 bar down to 830-ish bar. So you're seeing the pressure going down. Now if the hydrogen pressure is going down, well, where's it going? So for example, we had argued that the solubility of bulk nickel hydride is diddly squat. So we know that the hydrogen is not going into the bulk nickel. So where's it going?
Is that minimum of
This is millibar, 1,000 millibar, 1 bar, roughly in atmosphere. So somewhere near an atmosphere, and the pressure drops down to sub-atmosphere. So I was looking at this, and when I saw this, this really caught my attention because it meant their sample's absorbing hydrogen. How does their sample absorb hydrogen? What makes it absorb hydrogen? You go back and you read and talk to people and so forth, and they have a loading protocol to prepare their nickel. So what they do is they introduce the hydrogen, they heat it up, then they let the hydrogen go out, and they try loading it again, go through cycles. So pressure, depressure, elevate the temperature, burn off the oxide layer, and go in and out. And it might do from 6 to 10 times cycling. And what they see is that on each cycle, the loading increases a little bit. So by the time that they're done with their cycles, they're getting a substantial amount of loading. Let's think about this. Bulk nickel doesn't load much. You need a lot more pressure to pressure load bulk nickel, and they're certainly not doing that. But they get some loading anyway. So the number of atoms they're getting absorbed in one of the numbers deduced from their data is this number. The amount of nickel atom in the sample is this number, and you look at this and look at this, and it's sort of close to 1%, which is way the heck more than bulk nickel can load. In a paper by Camerota and colleagues who basically looked at the same system, they cycled it lots of times. They got a loading up to 0.2, nickel hydrogen 0.2, so 20% loading. And these numbers are phenomenally large. If you look at this, you just can't be anything other than astonished. So it has to be non-bulk loading, which means there's special sites, which means defects or impurities. Now, if you're going through the cycling, you're cycling hydrogen in and out, does that introduce impurities that make it into the nickel? I didn't think so. I thought defects. So not enough impurities in any event for the Camerota.
But did the lattice expand in this?
We don't know. Takeaway message. Pantelli co-workers pioneered nickel gas loading, elevated temperature operation, good excess power, and we get H2 loading. And basically the conclusion I came to is the following. We'd argued earlier that when the H goes into the nickel that it segregates. You get little clumps of high loading. But they're operating at elevated temperature. At elevated temperature, they're high enough where the vacancy diffusion coefficient is high enough to actually do some good. So the thinking is that they're actually, during their loading cycles, they're making Fukai phase. And the Fukai phase has defects, and the defects, the solubility is much higher, so it's giving places where the hydrogen can go. And that's why the loading is increasing. And it gets more and more, Fukai phase material for each cycle, just simply because once you've made them, they're stable. And if you load someplace else and you segregate and you get high hydrogen someplace else, you get another place where you get Fukai phase. Takeaway message. I'm looking at the clock, so I'm busy running very fast. Questions? Okay, so is nickel hydrogen like palladium deuteride? So I'm wondering whether Pantelli's gas loading nickel hydrogen is like the palladium deuteride experiment. And if you like, we were arguing that in the Fleischmann Pons experiment, it seemed like the whole point of the protocol in Fleischmann Pons experiment could be interpreted as making Fukai vacancies for co-deposited palladium at loading above 0.95 on the surface. On Pantelli's experiment, according to this interpretation, the cycling is making Fukai phase vacancies and making a lot of them. We now know from DFT calculations that H2 and HD formation near oxide monovacancy is nearly identical in nickel as it is in palladium. They're sort of the closest matched of all the materials that were studied. This is what Deuteron found in his calculations. And of course, we could test for vacancies using thermal desorption spectroscopy, as I showed on 2 days before. H diffuses in nickel it doesn't diffuse as well as it does in palladium at the same temperature. But in Piantelli's experiment, the temperature's higher. So nickel does diffuse. And at the elevated temperature of the Piantelli experiment, the diffusion of hydrogen nickel hydride is very similar to the diffusion of H in palladium deuteride. So in a sense, the hydrogen transport in nickel sort of works the same way as deuterium transport in palladium in the Fleischmann Pons experiment. And we recall that miscibility gap in this, but there's no miscibility gap issue in the nickel hydride because there's no miscibility gap present. There's segregation, there's clumps, and there's nothing. So let me go back and look at the excitation. So what does Piantelli do to kick things on? I know that palladium deuteride, what was done back in the early 90s at SRI, was to increase the current density, draw deuterium in to introduce a deuterium flux. The deuterium flux itself, we argued, made optical, coupled to optical phonons and give you excitation optical phonons. Well, what the heck is this temperature cycling doing? If you like, you drop the temperature, you bring in more hydrogen for the vacancies for the part that's, or for the Fukai phase. For the part that's not in the Fukai phase, you actually just send it out. So you change the loading, and then you change it back to sort of what it was before. So what the nickel hydride has to do is it has to breathe out and breathe in, which means this temperature cycling is inducing a hydrogen flux. So deuterium flux in palladium deuteride kicks on excess heat, and in some cases kicks it on and it sticks on for a while. In nickel hydrogen, the temperature cycling is inducing a hydrogen flux, which is kicking on the excess heat. Now in this case, it's not causing optical phonon excitation because we don't have much in the way of optical phonon modes. They're delocalized. So that probably isn't important here. On the other hand, we can also cause acoustical, high-frequency acoustical mode excitation as a result of the diffusion. So excess heat triggered by deuterium flux in palladium deuteride. By this interpretation, excess heat is being produced by a hydrogen flux in nickel hydride produced by this thermal cycling. Note that pressure cycling is also observed to kick on an excess heat event in nickel hydride, which would have the same effect. You raise the pressure, more hydrogen comes in, you lower the pressure, hydrogen goes out. That's a way to induce a hydrogen flux. So, issue, is Piantelli's nickel hydrogen experiment responding to hydrogen diffusion? Well, it sure looks like it. And if so, then it's looking to me like the kid sister of palladium deuteride. The takeaway message. The takeaway message is that the Piantelli protocol under these interpretations looks like it's doing what the current ramp protocol is doing in Fleischmann Pons experiment. Questions?
Because the hydrogen is clustering within the nickel, is there a difficulty of getting the heat out? Is there a concentration of thermal grade? Is there a pattern of thermal differences through the bulk material? Do we know how close the clusters are to the surface?
Piantelli seems to argue that the effect occurs very near the surface, and the surface gets really beat up. He's published photographs of the surface, and it just looks like somebody's come in and bashed the heck out of the surface.
Really? But it doesn't decrepitate?
Doesn't.
It doesn't fracture, or decrepitation where material under hydriding actually comes apart over a period of time and flakes off. That is not observed.
I'm not going to say that's not observed. I don't know that that's observed or not observed. I know that the surface looks discolored, beaten up, non-uniformities on the surface, places where it looks like the surface was gouged.
Yep.
But I don't know if that's due to the effect of nickel.
Does anything interesting happen in either the nickel or the palladium lattice when you introduce a mixture of both H and D2, like does it preferentially, does the D2 tend to try to get together, I'm sorry, the H and the D, does the D try to get together, does it try to go on different sides?
There's a very minor difference. For purposes of discussion here, we'll think of it as being equivalent in the lattice. So let me think about the phonon modes. So H solubility is low in nickel. Can't support a delocalized optical phonon mode without a lot of H. So if not optical phonon mode, then we'd expect compression acoustic mode operation. Fractionation seems possible for transverse modes, but the compressional modes, as we argued before, would have an advantage of being able to bring the atoms of the molecule a little bit closer together and make a change in the tunneling. So here's what the phonon modes look like for nickel. Basically, they're higher frequency than in palladium, so you can go up to high 8 terahertz at the top of the acoustical phonon band, which in my view would be the preferential place for the system to work. Donor-receiver mode applies. We'd expect the donor transition to be HD going to helium-3. The receiver transition would be nickel. Acoustic mode, phonon excitation. We drove the acoustic phonon modes. They would be exciting. That's where the energy should go in this. The fractionation in the nickel is imperfect. And so I'm thinking that that gives the possibility within the model of basically accessing unstable states in the nickel and leading to disintegration. Now in Piantelli's experiment, near the surface, I see nickel, I see iron, calcium, potassium, chlorine, sulfur. I see all this stuff. And all this stuff in this particular experiment sort of largely consistent with the picture that your nickel's handling this energy to fractionate it, so that HD going to helium-3 is about 5.5 MeV. So you've got a fractionated 5.5 MeV quanta down to 8 terahertz or so. Most of the work's then in this picture is being done by a nickel. It's done to states which are clean, but you have transition to states which basically can dissociate, disintegrate. So you're losing your nickel. And this, in my view, is an unwanted result of having an acoustical mode operation. So evidence for elemental anomalies in the Piantelli experiment. There's also massive charge emission, which they observed as well. Conjectures that nickel disintegration is an unintended and unwanted consequence of acoustic mode operation. Nickel disintegration is endothermic, so it's taking away from your energy you're producing. In palladium in hot spot operation, I think that's acoustic mode operation. I think it's hot because palladium disintegration is highly exothermic, so it's making your exoheat a lot larger. And there are elemental anomalies reported in association with the hot spots in palladium. Other relevant work, clocks ticking down, is Adamenko and Vysotsky in connection with proton 21. So they take electron beams, say a few hundred kilovolts, very massive, high density, high fluence electron beam going through materials, and it appears to induce transmutations. I think it's sort of a similar kind of thing. You know, car boot vibrations cause nuclear excitation. Well, if you have much more vibrations, much more energetic stuff going on, higher frequency, you go up higher, you access states which are unstable to disintegration. You can lattice-induced fission kind of process. I think proton 21 evidence supports that, or is consistent with that. And Diddig and Wisniewski have stunning experimental data that you just got to go look at. They take palladium deuteride at Dubno, they're running a gamma beam through it, and they're seeing massive transmutation. It's a macroscopic fraction of palladium, turning it into a slug of other elements. Takeaway message. H solubility in nickel's low, no delocalized optical phonon modes. I think internal transitions in nickel do the fractionation. You get nickel disintegration is an unintended consequence, which, by the way, underscores the importance of Celani's work, his working with Constantine. And it's a nickel alloy, which is cheap. He works on it in fractionated, but the solubility of hydrogen in this stuff is very high, which means you have the possibility of having an optical phonon mode, which means you have the chance of not disintegrating the nickel. And there's Celani doing a demo of his wire at National Instruments Week. Let me pause for questions or comments.
I read there's also copper in his isotope, Constantine. And is there any role copper plays?
Well, basically, anything that's in there that's moving is going to contribute in proportional to how strongly it's coupled and how many of them there are. So, yeah. Okay, so deuterium occurs in ordinary water at roughly 1.6300 hydrogen. So you're not going to expect very many HD molecules. So that's oftentimes used as an argument to say all this HD to helium-3 stuff is just wrong. There's no D. On the other hand, the reduced mass is lower than for D2, so the towing matrix element's quite a bit reduced as compared to D2. So the reactivity is much higher for HD going to helium-3. You could say, well, there's no observations whatsoever of helium-3 gas phase. There are no relevant experiments that have been attempted, as far as I know at this point. I'm very interested in knowing whether HD to helium-3 is responsible for excess heat. So dear Santa, my wish list, I want a measurement of this. I want to know what happens. Now I'm going to take the liberty of presenting a version of Mitchell's data. Mitchell, as he mentioned, studied excess heat in nickel in NIH, and we were thinking about whether HD going to helium-3 could be possible. So the idea was, there's hardly any D in normal water. Let's add some D, and if the excess heat goes up, maybe that gives some indirect evidence that HD going to helium-3 is going on. So here's what happened. Mitchell added deuterium to hydrogen, and here's 0, here's 4%, here's 8% over here, and at 3 different input power levels, the excess heat is going up with the addition of deuterium. So I look at that, I say, very interesting, very interesting. So this provides indirect support that HD going to helium-3
is palladium.
Sorry, what?
The matrix is palladium.
I believe this is with nickel.
Yes.
Takeaway message. Not much D in light water. Don't know whether HD is giving us excess heat. Mitchell's experiments support the notion that HD to helium-3 may be what's going on. We really need helium-3 gas measurements. I'm going over and I can't continue tomorrow. Mitchell, I apologize. I'm actually close to being done. In the Piantelli experiment, they reported observation of a gamma ray at a low level. This is at 661 keV, and it appears in correlation with the excess heat production at very low levels. This at the moment is not understood, but it's interesting. Very interesting. The level is sufficiently low that you wouldn't have to worry so much about it if you're making power and you've got one of these things running in your basement. They have a little bit of neutron production as well. That you might have to worry a little bit more about. This is not understood at present. Okay, I want to think, sort of my last topic, I want to think a little bit about commercial applications in nickel hydride. So the importance of the nickel hydride is that nickel is cheap, palladium is not. The Piantelli experiment is important because it's a significant amount of excess heat, nickel-based. If you believe that helium-3 is made, then you have the same issue for helium-3 removal as in helium-4 case with palladium deuteride. So this favors higher temperature, and I'm going to put in parentheses, at higher temperature you have issues with loading, so you want to make sure that the temperatures you go to, you can still get what loading you need. And it also favors smaller scale nickel. So nanopowders, or powders or nanopowders, if there's less distance between your monovacancy and your surface, then your power density is going to be higher if you've got a small structure. So what this suggests is that working with big nickel bars, you get some advantage if you went to nickel powders or nickel nanopowders. Before going there, he remarked that at the Pontignano workshop, Bill Collis got up and spoke for Piantelli and reported observation of a nickel hydrogen cell to run in self-sustained operation at 280 C, consistent with about 70 watts of output power, and ran for 8 months. Thank you. On the internet, I was looking around last night, apparently at the Atom Unexplored meeting, Ciampoli talked about 200 watts for 55 days, if I got my numbers correct. So this is not a unique report from the Piantelli group. But basically, what Collis said was done is you cycle it, you induce some excess heat. Actually, I think Piantelli told me this, but then once it's getting excess heat, you can cycle it again and induce more regions to turn on, and cycle again, get more regions going. They kept on doing this to get the heat up to the point where they could turn off their heater and the thing stayed hot and continued to operate.
You say 70 watts output power. Is that excess power, or is that just sort of output? That's sort of input plus the excess.
Self-sustaining. Input
Okay.
turned off.
Got it.
This is really important. Okay, Piantelli and his collaborators say they worked with nickel powders and nanoscale powders starting from around 2000, motivated by Arata's papers. Arata, we recognize, pioneered nano-structured palladium for Fleischmann Pons experiments. Rossi claims independent development of nickel-hydrogen powder experiment, claims reproducibility, high energy gain, high output power, commercialization underway, and Defcalian also claims commercialization is underway, also nickel-hydrogen systems. I downloaded a picture of the ECAT from the ECAT website. For those of you who are interested, here's, well, I refer you to the ECAT website. This is, again, from the ECAT website. This is a picture of what their 1 megawatt system looks like. Their 1 megawatt system basically has a lot of the smaller systems stacked up in banks along the shelves. They take a lot of, say, 5 kilowatt systems, put enough of them together, and you get yourself up to megawatt. I think there was a demo where this was claimed to actually produce power somewhere near half a megawatt, over half a megawatt. So publication, Kim and Haji Christos from the ICCF 18 proceedings of the Hyperion reactor. And this looks unlegible. I think the nickel hydride's inside. I think there's heating coil. There's a heating thing and a cooling coil. Here's results from a run that they've done that was published in the same proceedings paper. The claim is a power gain of about 3. In Piantelli's early nickel hydrogen runs, it was 40–50%. Later on, it was the nickel bars was factor 3. Here, the powders is claimed to be factor of 3. What I want to draw your attention to is 7 kilowatt. Where's the power level? So input power is in red. So here's 2 kilowatts. Output power is green, so here's 8 to 10 kilowatts. So we're not talking about a little cell, none of this 100 milliwatt stuff. This is like industrial scale, but which is the advantage if your nickel's cheap, you can do an experiment like this. I apologize to my colleague Kim. I've stolen one of his view-graphs from ICCF 18, which shows some of their nano nickel structure. And here's the nano-nickel. It goes into a vessel, and off you go. So there you have nickel and hydrogen. You have a flame of excess heat under conditions which is commercially relevant. Takeaway message. Based on work published by Piantelli Group with nickel and talked about at conferences, you would expect to get 3x excess heat from high temperature nickel hydride gas experiment. Of course, as we've discussed, they've described self-sustaining mode, which more than 3x excess heat. It's infinite excess heat because there's no input power. Limited by helium-3 accumulation, you would expect higher power density in small scale nickel structures. That seems to be the case, as what I can tell. I guess I'll have to hear from Mitchell whether his experiments are consistent with it. Nickel's cheap. Lossy claims high reproducibility in commercial products forthcoming. Callium claims high reproducibility in commercial products forthcoming. Piantelli, the originator of the technology, is involved with Nick Energy. Nick Energy doesn't talk at all. Robert would kill me if I didn't at least give a plug for him. Robert Godis is working at Berlin using an axial current protocol. They've reported results in nickel hydride and palladium deuteride, and they're working on a product for commercialization. Conclusions. So this is conclusions sort of like for the whole thing. Many negative results early on, effect inconsistent with known condensed matter nuclear physics, Zinga's 3 miracles, argument, claim of excess heat rejected by the scientific community. Field delineated as not part of science back in 1989, pretty much. Quarter century of attacks on the field. The number of researchers left now is a pale fraction of what it was, say, even back in 1994. Subsequent positive experiments, and we've talked a lot about positive experiments. Science in the field has found a way to move forward in spite of the obstacles. Excess heat amenable to scientific investigation. As we've argued, we've been using other areas of science. We've been using electrochemistry, physical chemistry, physics, and so forth to come and try to understand the Fleischmann Pons experiment, try to get some intuition as to what's going on. We've put forth a picture as to what's going on for excess heat. We've now described a theoretical approach which looks encouraging, and if you like, which is based on known physics, standard model being known physics. And if you like, all that we've done is said within the standard models, there's a little bit of fine print associated with the generalized fold-level twos and transformations, so that you shouldn't use it like everywhere. You've got to go ahead, if there's loss, and be careful where you use it and calculate things more carefully. Picture allows us to begin understanding the PDP system, also nickel hydrogen system. And nickel hydrogen systems receiving a huge amount of attention these days. We would expect nickel hydrogen powder to be able to produce excess heat. The efforts to commercialize, which are uniformly being dismissed at this point, should not be uniformly dismissed. Some of them should be taken seriously. What we need is a serious and sustained scientific effort to understand what's going on. The world's facing serious problems. The technologies based on the new effects actually have the potential to provide solutions for some of the big problems, not for overpopulation, which is driving our problems, but maybe to give us some time. The barrier to scientists entering the field. Who wants to join a field where you're going to get shot down and have your career destroyed? There's essentially no funding available at present. People were really excited recently because there was a DOE post saying that ARPA-E was going to provide, was interested in getting proposals in the case of LENR. So a lot of people have been saying, well, things are changing. Maybe there's the possibility that funding's available. Here's an email from ARPA-E. I guess the answer is that things aren't really changing. Warning, working in this field can and will destroy your career. And here's Fleischmann and me back in better times and when I still had some hair. Comments, questions? Any? Ed, I apologize to Mitchell for going over. Let's take a few-minute break and then we'll reconvene.
Today, as I told you, we would talk about nickel systems. And we're going to talk about two things. We'll talk about aqueous nickel systems, the fact that we are able to get excess energy out and get the cold fusion system to work. And actually, one of the things I'd like to see from you, Peter, is with your theory, maybe you could tell us about how it's predicted whether nickel should react quicker and whether the heat after death should end quicker. And then we'll talk about the impact of deuterons on the nickel system. And we'll show both that with the nickel system there can be degradation, catastrophic degradation of the nickel. And then I'll show you the latest NANORs that we're making, which are nickel with deuterium. Okay, so first off, this was the report that Peter discussed to you, where we took ordinary water with a working nickel system. So we have platinum as the anode, we have ordinary water around nickel fusor, which is the cathode, and we begin adding, that's ahead a little bit, oh boy. We'll come back to that. Let me just first show you the nickel systems before we add the deuterium. So here we're running a nickel system over time. We're looking at the power input, which is here. Here's our background noise. As I told you, we always measure noise before we run the experiment. So this is in log watts here. We do an integral to get the total energy of the system, which is here up from 0 to 200,000 joules. So here, for example, we wait 10 hours, measure the noise in the system. Then we run to the ohmic control. This is a resistor, a carbon composition resistor, or a wire-wound resistor that's next to the cold fusion device and allows us to calibrate the system. Here's our input, here's our output. It's a nice match. But when we run the cold fusion system, we're getting excess energy out. Here's our input, and now we're getting more out. And as I told you before, when we look at these curves, we see that we have parallel systems for the ohmic control, but when we see cold fusion, we see a superlinear rise. And the reason that it's not linear here is we're looking at different levels. This system was where we have nickel, ordinary water, and a gold anode. We did a lot of, if you go in the literature, around 1998 to 2000, we reported a lot of the differences we saw with gold versus platinum. Here is the more conventional nickel, ordinary water, platinum. The fusor is in the nickel. So here, for example, for the first 8 hours, we measure the background noise, which is over here, nothing higher than, it looks like 10 milliwatts. Here's the ohmic control. We put in here, we get out here. We put it in here, we're getting more out. And then we put in two more ohmic controls here. Again, we get less. And again, with the nickel cathode, we get more. So we have two thermal spectrographs of two runs, one with gold as the anode, one with platinum as the anode, but both with nickel fusor, so we get excess heat. Now, this was actually, I went back, and this is one of the first ones where we found the peak in one of our nickel systems. And after that, I'm going to tell you something a little about a history here. We call this the optimal operating point. But I have to thank Peter for that. We actually had a terrible name for it in the beginning. When we plot input power, which is how we see these, so we look at V times I input power in this direction, and we look at our output, either helium for production, incremental production, or excess energy, and we see something like this. Well, it turns out, every now and then, we saw something come up there. It didn't always go down, so we actually called it a pi notch, because it looked a little bit like pi, and we would settle it over here. And I'll come back to why that's important, even though we call it optimal operating points now. And the reason is, some of these systems appear to have incredibly high energy gain at low power. We're going to show you that in a moment. Okay, let's go back to this. So here we see an optimal operating point. We're looking at log input power. And as we talked on Wednesday, I think this is a key to why most people miss cold fusion. On this side, inadequate loading. On this side, overdrive. And then there's the other issues that Peter also mentioned. Here too, we have a nickel system where we see a very high excess energy over here. And in fact, we use these on Stirling engines, as I showed you. I'll show you a couple of more pictures of that. And basically what we have here, I'll put a video on in a minute, is one of these has the fusor in it, where we're driving the cold fusion system. The other one has an ohmic control. These will be in electrical series. We'll measure the voltage on both. And in the end, what we'll see is we'll have less input power, DC, to the cold fusion device, but we get more output. And this is a close-up inside. And these are some of our runs. Now, it turned out this is heavy water with palladium. This is ordinary water with nickel. And we were getting energy gains a little bit better than 30%, which is what we were just hearing. And when we get, we didn't really talk much about it in this course, but the open circuit voltage is our indicator of how well we did the cold fusion. And we could talk about this for another 2 days. And it turned out it also played a role here. I showed you the fuel cells that we did. Remember we talked about we tried to do the feedback loop for electricity. We found that we were not able to do it because of burning up losses going around. And also I mentioned the fuel cell. I just showed you what we did it in. We had a little car. And it was cute. It had a little thermoelectric converter. And this was actually done 11 years ago. And then after this, we decided we would spend a little bit more time trying to improve the gain rather than putting directly into commercialization. And this was the data that we talked about very quickly the other day, where we were trying to go around the loop. We learned about the massive losses when using the fuel cells. That's just our circuit. Now, the other thing is, Peter mentioned this paper, and let me show you what we used. Here was one of these fusors. So we used this as the cathode. This is a nickel material. We put it in ordinary water. We have platinum as the anode. We drive it and add increasing amounts of heavy water. And what we ended up doing, we did 3%, 7%. Peter showed you those curves. And so, for example, here again, we do the noise measurement. We do the ohmic control. We get a nice match. And we do various levels of adding heavy water to the ordinary water. Yeah? Okay. And basically, we got higher power out for all increased amounts of D2O added to the ordinary water. But we discovered something else, and that's why we spent a lot of time looking at palladium after that. We damaged the fusor. At high deuteron levels, high deuterium concentration levels, at high drive levels, the nickel became irreversibly changed. It turns out that this is its incremental resistivity. It dropped from 8.8 microohm sonometers down to 8. The color changed. This is an irreversible change, but if you're going to build a commercial system, it's even more important, because here's our new fusor where we're having an energy gain up here, and once we destroy it, it's done with the control. It never worked again. So we're able to take an active device and not only quench it, but irreversibly destroy it. Here's a close-up of that. And so, for example, here we do the boost, we get more out, and then if we drive it too far, we come down here. It never comes back. Questions?
What is the ratio in the y-axis? So is power?
We're looking here at power gain. So here's a 50% increase. Here's a 100% increase. So the power gain here is 2. You got to subtract by 1. This says 1, so it's actually no gain. Okay. So it's 1 minus the amount is what the increase is.
And below 1 means?
Means it's a loss. We're dissipating. This is not even recovery when you go below. We did not even get it back. Our controls, you see, here's 3 controls. Ohmic controls, we're very close to 100%. So we're actually probably inducing chemical change within the nickel as we're driving it. And
Because
so
if not, you should get to the one.
Peter said it's endothermic. This is where it's going. This is one of his predictions that turns out to be correct. Another one that turns out to be correct. Okay. All right, we made a company called Nanortech. These were the NANORs. These were our Series 7. Basically, the Series 6 was the one we showed at the demo back in 2012. These are hyper-loaded zirconium oxide. The one we showed at the demo was palladium nickel with deuterium added. We looked not only at that, but in Series 7, we're looking at a half a dozen other nanomaterials. So we're still evolving means of loading, developing materials and their response. Essentially, these are two-terminal devices like a resistor. We put in a DC current. I showed you there were problems, and I'll show you more with respect to catastrophic changes in the impedance of the device, but we get out excess energy. Now, here's how we're going to read these devices. All of these, we now add calibration pulses, as I told you, so we can calibrate the equipment for both current and voltage. Then we do an ohmic control. So here, for example, is our control input and our output. And here's our input to the NANOR, and here's our output. And they're all going to be like this. So let's look at 7.2. Here, for example, here's our delta T divided by the input power, calibration pulses, calibration pulses. Here's our input power. Here's our delta T. Here's our input power here. Here's our delta T divided by input power. Yes?
Are these palladium? Is these nickel? These mixed? What?
It'll say what it is. This 7.2 is PDNI. As we go to higher numbers, we switch to Ni alone.
Deuterium or hydrogen?
Only deuterium. Every one I show you in Series 7 is D, but some of them are NIPD, and as we go to higher numbers, they're just Ni. Okay, so the ratio in gain, energy gain, is here to here. That's a little bit more than 30%. Okay, 7.4, here some of these results are so large, I have to use log plots, which is sort of sweet. So we're looking at delta T over Pn, and what we do, here's our input power to the control, here's our input power to the cold fusion device, here's our output power, our output, this is input power, is read off this side. This is output, which is delta T divided by input power. So if you want the ratio of energy gain, it's this to here. And what's that, 1, 2 orders of magnitude? Not too bad. And it's over and over, it's reproducible. So here, input power to the control, to the NANOR, to the control, to the NANOR, control, NANOR, over and over. And the energy ratio is here to here. Now you see there's a fall off. As we go to higher power, the gain now here is just about a log. But we're up here, we're up to 2 or more logs, okay? Questions? Please.
In your highest power gain experience, is the high power gain essentially because you reach the same power level with much less input? Or would you more say, well, with the same input, I'm reaching much higher output?
As a matter of fact, I think you are right on. I think we not only have issues of loading, of secondary reactions, but there may be a limit to how much power we get out of these devices. And we may be swamping them. And what we may be seeing here is in the very low levels, the maximum amount they can put out. Yes?
Are you dealing with low mass, like 50 milligrams or so?
Less.
Like
Less. These are about 30 milligrams. I'm sorry, I should have said that. Our NANORs are very small. I mean,
so isn't the power level that you're saying, even though it doesn't look so high, isn't it fantastically high for such a low amount of mass?
It is. We're running between 19 kilowatts and 60 kilowatts per kilogram of material, which isn't too shabby.
Could you repeat that? 90 kilowatts?
It's between 19 and just under 70 kilowatts per kilogram is what we're getting out for power. Power density. Pardon?
Can we clap?
And just
All
one
right,
more
here-
question, sorry.
Sure.
Those kilograms, are they the nanor kilograms or the active PD?
No, this is calculated. There are no kilograms. We have milligrams.
Right.
We have 30. I think the biggest nanor we're running right now is about 150 to 200 milligrams.
But you have zirconium oxide as well as the
Yes.
nickel. So how much?
Okay.
So how much?
On the basis of the whole mass,
Yes.
that's the 19 kilowatts per kilogram. On the basis of the palladium alone, that's where we get around 68 kilowatts per kilogram. It goes from 19,000 to 68,000. Okay?
I'm just calculating.
That's based
What
on
the prices
duty-
earlier.
That's whether you have the whole mass or just the palladium. Okay, so here's another one, 7.4. Input to the control, input to the nanor. Here's our, let's see, this one's delta T over P, and again, we take the ratio to get the energy gain. Here was our, let's see, this was, okay, 7.4. So what we're looking at here, this is input, and delta T divided by power. Again, we take the ratio. The ratio of energy gain is this to this. And this is a linear plot, not a log plot. I think the importance here is that we were trying to go to higher power. At MIT, the most we had done was a couple of hundred milliwatts, and what we went up here was to 2 watts. So we're trying to increase by orders of magnitude our nanors over time. And so, for example, here, this is 6.4. We're driving it at 610 volts. We're getting a power gain of 3.6. That's our impedance of the nano. Yeah, go ahead.
I apologize. If you go to higher power, do you increase the mass, or do you still have a low mass here?
I don't change the mass right now.
So you're
we've
driving
never
a different regime.
Yes,
Driving-
we've never. We limited the input drive in your office, and now I really don't care if I destroy them. So we're going higher.
So you're going into the avalanche regime here.
Actually just up to it, and as I'll show you, we have our first pictures of going through it. That's coming up. Okay, so here's here again. It's the instantaneous power gain is the ratio here. We got 3.6, and we went up as high as 1.5 watts input. And at 1.5 watts, it's equal to the resistor. Remember that optimal operating point comes down. So you know you can't run this nanor. You don't want to run it at 1.5 watts. In fact, maybe what we want to do is very tiny input and millions of them. Okay, 7.7. Here's another one where I think this one is solely nickel. There's no palladium in this. This is pure nickel nanomaterial added with D. Then here's our calibration pulses, our ohma control, input to the nanor, which again is nickel with D, and our this is just delta T. We're looking at delta T. Delta T, delta T. And here when we normalize the delta T by the input power, we can take the ratio. So we sort of match the impedances here to here, and that's our ratio.
So Mitchell,
Yes,
does your hyperloading trick work on nickel?
it does. I didn't know until this, yes. Yeah, so for example, here's 7.7. We're driving it at 450 volts. We used to use water in the core. It was Gail's idea to switch to paraffin. It's been a great impact. It's helped a lot. And so here, for example, you can't really compare because it's input power and delta T. You want to divide by input power, and I think we do that in the next one. Yes. So the ratio of energy gain is going to be delta T over P into here to here. Here's our energy gain. And that is a couple of orders of magnitude too, isn't it? 4, 3 or 4. Nickel nanomaterial. No clapping till we get these out. Commercialization, we've got a long way to go. Here again, the input power normalized. This also is with the only nickel with the D, and again we take the ratios. By the way, this is not with the delta T. This is the corroboratory measurement where we look at heat flow. Like I told you, we'd like to see 3 things. We'd like to see the delta T rise, we want to see the heat flow increment, and then we want to do the full bore calorimetry. So here, the heat flow also had a gain of beyond 2 orders of magnitude. And here it gets really exciting. Up until, well, this is the first time I've been able to go through the avalanche and not blow up equipment and check my pulse, make sure we're all okay. Up until this, it was always we had seen one side or the other. And this is the first time I'm going to be able to show you what we saw. So here's the control. What we're looking at is input power, delta T. And remember, you won't see much until we switch to thermal power spectroscopy. But you can see a little bit here. Control pulses. Here's our input. Here's our delta T. Here's our input here. Here's our delta T. And after the avalanche, let's do the calorimetry. And here's what we find. Ohmic control, nice match. Excess energy, more. Post-avalanche, less. In fact, when we plot the instantaneous power gain for cold fusion for the nanomaterials, the ohmic control comes out at 1. No surprise there. The excess energy, we're doing a drive here now. I think this is on the order of a fraction of a watt. We're driving it at a little bit over a kilowatt.
Kilovolt.
Pardon?
Kilovolt.
Yeah, kilovolt. Thank you. Take a break here. This graph took a long time to get. So we have 5 levels of input electrical power here. We're going from a power gain of 5 to 2. We go through the avalanche, and it's just like the resistor. Okay? We had seen this before, that when we go through the avalanche, we're creating other, perhaps competing processes. But here, it's absolutely clear to go through the avalanche and we lose our excess energy. Anyway, we did it a few times. And we also saw it for heat flow. Again, we take the ratio. This is before the avalanche. Here's after the avalanche, so we lose our excess energy. Here we can see that if we stay below the avalanche, see, here's our input-output. Here's the input to the NANOR, and the output, again, this is the nickel with the D, no palladium in this. Our energy gain is here to here. When we drive here, here to here, here to here, it's falling down. And therefore, these slopes are also falling. And eventually, if this came down to match, these two would be parallel, like they are here.
What temperatures do you reach at this high power mode driving?
We're still clamping at about 10 or 15 degrees above room level. We're ready to go higher. I wanted to get as much data out of it as I could. Okay, 7A. This is just more. Let's see. Again, this is just delta T. You can't do it till it's delta T over Pn. I'm sorry. Here we go, delta T over Pn. So here's our input to the ohmic control. Here's our output divided by power in. Here's our input to the NANOR, output divided by power in. This ratio is our energy gain. This one has both PD and nickel in it. But again, we can see there's a very nice energy gain here, and the gain falls off. You need to understand the optimal operating point manifolds, the fact that there's competitive reactions. And if you do it right, you see it not only with the delta T here with the heat flow, we're seeing a ratio of what, a decade and a half for heat flow increase. And here's the full bore calorimetry with this nice paraffin calorimeter suggested by Dale. And we have a energy gain of 20. So here's the ohmic control. No matter what level we do, we get a match. When we treat here, we see a great energy gain and therefore a superlinear rise. So what do we have? Our NANORs now can give up to 1.5 watts input. We're seeing 3 times input, 3 times output compared to the input at 1 watt input, and 27 times at 4 milliwatts. And when we go down less, it's even higher. That's what I showed you there. So we may not be designing these right. We still have to think about it.
Yeah. Mitchell, in other words, you basically are showing us the holy grail. You have a nickel-based technology, works with D2, hyper-loaded, and it gives great gain.
It does give great gain.
Why aren't you commercializing this?
Because it's small amounts. We have to figure out how to make more.
You make lots of small
Yes.
things together.
That's the definite way out at worst.
What are the thoughts why the your power output is not as it goes down with your power? Why the higher energy ones don't produce as much gain?
Well, the argument is that at low current density, the current goes from raisin to raisin to raisin, so the current goes where you want. You go into the high power region, you go into avalanche region, the current's going everywhere through, so some of your current goes through the raisins and most of it just misses it.
Just goes by and bypasses stuff.
Right. So instead of making those optical phonons that you need for Peter's model to couple, it's doing other things. All right, we're making Series 8 NANORs, which are going to be the high power. And here's the bottom line. Actually, we did this back. We should raise this to 40,000 or something. Quotes from Dune, if any of you ever read that. And let's see, one more thing I was going to show you here. Well, it's not important. It's the light. You were talking about whether the increase in energy gain when we illuminate the cathode was due to the incident beam. And we can show here it clearly isn't, because here we do the control in the laser, the control, the laser, and the fusor. Okay. Anyway, questions? Yeah.
Dr. Swartz, aren't these to the point where we can return to the experiment of Fleischmann Pons, give NANORs to different colleges throughout the country, and wouldn't they get positive, convincing results?
Did you say with the setup by Fleischmann Pons?
No, with using the NANORs.
That's the hope. That is the hope. We have to make more of them, and we are finding all kinds of problems with making them that I didn't expect. I don't have the luck of some of the other people in the field where it works all the time right away, but we were a little persistent. Yes?
Yeah. Have you taken some of your NANORs and put them on a lifetime test where they're just running continuously to see what happens to the output over time?
Well, we've done that inadvertently and unintentionally because we do different experiments like I showed you yesterday. So the one that we showed at Peter's lab in the demo 2 years ago had run for about a month, and we collected the data every day. We ran it in his office for 4 months, and then we did other work with it. So it's not, I haven't had the luxury of having one where we can just run it continuously. We've sort of been using it and collecting the data from each of the subset of experiments.
So you don't have another, a less ambitious and expensive protocol that you could use to put the NANOR under for a long period of time, and then after, say, a year, take the NANOR and then put it into your three-way heat-proof method. I can understand.
Well, I'd run it the whole time in the three-way.
Right, but you don't have those resources.
No, we haven't done that yet. This is actually the first month I've had more than one NANOR in hand. I mean, even though it's slow, we're making about one a month right now. In cold fusion for 25 years, it's always been you build a cell, you test it, 9 months go by, you build a new one. I mean, I've never had multiple devices before, so it's new. Yes?
Just so I understood correctly, what were the maximum power gains that you described in that last set of slides?
I'm not going to say.
But
it does.
Was it orders of magnitude?
Yes, it does appear to be. Okay, the test will begin in.
Can you show us the experiment you did with the Stirling engine connected to the phonon?
Yes. Yes, I got 2 of those if I'm lucky, if they survived. Let's see, we got 2. This was the first one I showed you. This is, sorry for the dumbness of it all. This is before we hooked up the control. I'll show you the control in a second. Stirling engine. So you can't believe this because there's no control.
Today is December 20th.
You really need both.
2004. It is 3 in the afternoon, Monday.
I was excited. Anyway, I'm going to show you the other one with the control.
This is the first cold fusion Stirling engine.
I think it repeated. How do I shut it?
Today is December 20th.
You have to get it back up.
2004.
You got to get it up to shut it? Thank
It
you.
is 3 in the...
Now shut it off.
Thank you. Looks like we all have a lot to learn from these things. All right. Here we have the control. And if it works, okay.
This is our light water Stirling demonstration showing cold fusion using nickel on the nickel fusor. On the right is the control.
More power on the right.
On the left is the fusor-driven Stirling engine.
We have about twice the power on the right. We were making more electricity on the right. It had higher temperatures on the right. And
this is our light water
we sent this down to the patent office, and they said, you did the same thing Fleischmann Pons did. So it's a... In fact, that's been what they've said about everything we've ever sent there. We sent them the nickel stuff. They said that's what Fleischmann Pons did. We sent a device for measuring loading. They said that's what Fleischmann Pons did. They sort of have a standard boilerplate they send back. Anyway, that's it. Any questions?
Just to understand the latest test you showed us, those were purely nickel nanos with light?
No, they were nickel nanomaterial, but they had no palladium in them.
No palladium?
No palladium, just nickel.
And with light water or with deuterium?
Only deuterium for these.
Only deuterium?
Yes, there's no light water in this. In fact, great effort is made to keep light water, ordinary water out. We have no light water.
So let me put in a request. It'd be fun to have a mixed HD nickel system and see what it does.
Well, I think what our plan is in the next year is to do the whole group. So we'll have a PD nanomaterial, a mixed, and NI, and then find out what each of the outputs are peak. I think one of the advantages of the optimal operating points is by knowing the peak, we can compare systems. And without that, you really can't.
So zirconium was again cookie dough for that nickel nano.
Yes, there's no zirconium in the ones half of the ones I showed you had zirconium, but the earlier ones didn't. 7.8 did, had zirconium. 7.4 did, the other ones did not. Again, we're trying new materials, new setups. I wish I could tell you more, but we will next time.
The advantage of zirconium was to prevent sintering and also to remove helium flow out of metal.
It prevents the sintering and it acts as an insulator. A massive insulator. That's why when we make these, before we activate them, sometimes they've been as high as 10 to 100 terohms, which is very tough. You put them into a circuit board, and everything that you think is not connected, it is connected compared to your device. It was actually the reason why when I brought the device to Peter's office, we had a beautiful box. And then I realized we can't use it. We have to build this whole thing in the air to keep the leads far apart. And that's why it ended up in that Tupperware crate inside Peter's office. It was an inadvertent and unintentional result of Murphy whacking me.
Yttrium stabilized zirconia.
Pardon?
Is it yttrium stabilized zirconia?
Is it easy to stabilize it?
Yttrium stabilized.
Oh, I haven't tried that. I think Dennis Cravens uses some of that material, doesn't he? No?
I don't know.
Did you find it successful?
No, because normally also zirconia is not very stable, so there is a small amount of yttrium to stabilize.
I better look into it. There's a lot of it. Thank you. Well, I guess that's it. Do you want to say anything else?
Well, we have the exam.
Well, we're counting on all of you, okay?